So we are live.
Okay, so welcome everybody to the last session of COMSNETS 2021. So today we have two esteemed speakers, Dr. Vinosh Babu James from Qualcomm and Dr. Sendil Kumar from Ericsson. So they will give a tutorial on 5G new radio deployment issues related to that. So before they start, I will briefly introduce them. Dr. Sendil Kumar is a general manager in standardization and spectrum in government and industry relations at Ericsson. He is currently responsible for leading standardization and spectrum engagements in India. He works closely with the national, regional, and global working groups related to standards and spectrum matters. He actively contributes in developing national proprietary views forwards the ITUR, APT, AWG, and WRC. He actively contributed in the IMT 2020 evaluation process and in the development of rural test environment requirements in IMT 2020. At Ericsson, he is focused on future spectrum issues that are the subject of the World Radio Conference and support for technical studies. Prior to Ericsson, he worked with research organizations including Samsung R&D, Sensor Center of Excellence of Wireless Technology, and Telecom Center of Excellence. He had contributed to standardization development in both 3GPP2 and 3GPP for HRPD, HSDPA, LTE. He also has a career stint as a mentor in a patent service organization dealing with patents for 4G standards and high-tech industries. He was awarded PhD degree in wireless communication from IIT Madras. So a very hearty welcome to Dr. Sendil Kumar. We also have Dr. Vinosh Babu James from Qualcomm. So he leads the technical standards engagement from Qualcomm in India for Qualcomm in India. Over the last 15 years, he has participated in technical standards engagements at the ITU, the 3GPP, and the IEEE. He also engages with Indian and regional stakeholders on matters related to radio standardization, harmonization, and regulation. Vinosh joined Qualcomm in 2011 and has served in several roles spanning engineering and standardization. He has his PhD in electrical engineering from IIT Madras with a specialization in wireless com. He has held several technical roles, including serving as the chairman of the 5G working group in TSDSI and currently as the chairman of the Future Communication Technologies in TEC. He holds several patents and international publications to his name. He is also a senior member of the IEEE. A very hearty welcome to Dr. Vinosh also, and we look forward to hearing to your tutorials. The stage is yours. Thanks.
Thank you very much. Just confirming if my audio and the screen, they are okay.
Your audio is clear, but I don't see any slide on the screen.
Now?
Yes, perfect.
Okay. Thank you very much. Good evening to the participants. Thank you again very much to the host, both Professor Arpan and Dr. Nadeem. Happy to be in here today delivering this tutorial. So we have like a 5-session pack where we are going to talk about NR deployment considerations and its continued evolution within the 3GPP. So as mentioned by the host, we have two speakers. Me, I come from the Qualcomm background, so I deal mostly with devices and end user equipment. And Sendil comes from Ericsson, has the infra background, base stations, network, and other feature things. So we are going to mix topics and see, how best can we leverage each other's expertise in actually managing it. Going by what is there in the left, we have 5 sessions. So I'm going to begin with 3GPP.
Dr. Vinosh, can you hear us? It seems we have lost connection with him. Dr. Sendil, you are muted, I think. So you are trying to speak, say something.
Yeah, let me try to reach him out.
Okay.
Yeah, yeah. Meanwhile, he joins. Yeah. So basically, the way we organize this is so we have the sessions alternatively arranged. So Vinosh will start with the background of 3GPP work and what are NR fundamentals, and then I will jump on to explaining spectrum-related topics about 5G, and then Vinosh will again take on to deployment options available in 3GPP and how a typical deployment will happen in the real world, and then I'll be continuing the session too. And session 5, we have an interesting presentation from Vinosh, what he will explain how 5G will play an important role in Industry 4 and what are the specifications that actually were introduced into 3GPP. So I think it'll be good to stay till the end and watch the last Industry 4 presentation from him. Good. Let's see if he's in. I think he's still not connected.
Not yet. So okay, if I think if the connection terminates, then the host actually has to include him again in this stage. So Gavini, can you hear us? So can you just check whether Dr. Vinosh is in the audience? Yes, he is in the audience. So please add him to the stage. Please invite him. Yes.
Yeah, no, he is in the stage. Like
He is in
it's
the stage.
getting connected. We need to
Okay.
wait.
It seems he was speaking and we are not able to hear him.
He is still not able to contact us.
So this is one reason, Sendil, we need 5G.
Uh, Nadeem, I don't think 5G will solve this unless the network does not reach to the home, right?
Okay, I see Vinosh is back on stage. Vinosh, can you hear us?
I can hear you guys now.
Yeah.
Yes,
So
if the connection speed is an issue, you might think of switching off the video in case bandwidth is
yes.
playing any.
I'm actually seeing north of 120 Mbps speed, so I don't know what is the issue.
Okay, so let's get going.
Yeah. So
Okay, so
actually,
I need to start again, right?
Yeah.
I
yeah.
was sort of
From the
speaking to
beginning.
myself.
So Vinosh, I already walked through the outline of the tutorial that we have. You can directly jump into session 1.
Okay, you shared this current screen also, right? Is that correct understanding?
Yes. This is what. Yeah, you
Okay.
can. I'll go mute.
Okay, cool then. Thank you. Just to put things in perspective, we are basically sharing our experience with you guys in here, not necessarily sharing our employers' views. So we may have things which are in alignment, we may have things which are not in alignment. So if there are things not in alignment, don't count it on our employer. It's basically us trying to share our experience and knowledge with you guys, discussing these aspects. Okay, so let's let's get into the basics of standardization and why we end up doing it. So if you look into the whole aspect of cellular design, this is like 4 decade old, right? So right from the first generation of cellular systems where we did analog communication, but there was always interoperable, and there are these things actually its own time, right? But the way the revolution actually happened was when you moved away from the wired environment to the wireless systems, right? So how does that actually impact our life, right? So cutting the wires to the telephone was the first step, and the subsequent evolution from 2G, 3G, 4G, and now to 5G brought a wide range of new possibilities, right? So if you look into the Ericsson mobility report, it says that by 2025, you're going to see about 9 billion mobile subscriptions throughout the world, right? And a significant amount of them are actually going to use cellular for their broadband usage. So it's not going to be about smartphones alone. It's going to be a broad category of devices, network that will have to be used, right? So it's a game changer, the way how we will end up using it. So communications is based on technology standards, and it's going to be continuing to rely on technology standards. It enables an open competitive ecosystem where all players can access what's needed to be successful, right? So before new technologies can be commercialized in a mass scale, standards need to be set. First, it ensures inter-vendor system interoperability. What do I mean by that? A call from, say, example, a Samsung phone or an Apple iPhone, say powered both by a Qualcomm Snapdragon chipset, connects to a base station by a Vodafone Idea or a Reliance Jio or an Airtel, which can be supplied by any of these vendors, Ericsson, Nokia, Huawei, CTE, whoever it is. And then it connects in the background to the internet through a Cisco router or a Netgear router or something else. So each of these vendors in the puzzle, they come into the picture, they start developing equipment of themselves. This equipment then communicates with something which is not theirs. And for that to seamlessly work, you need technical standards, technology standards. And the second thing is, the more and more partners come into developing the ecosystem, which actually ensures that there is a harmonized manner by which more and more people consume these technologies. So it spurs a transparent and fair industry competition. And most of them are actually available free to download, like the way, the 3GPP standards are currently available. So how do we get into this whole design of standards making, right? So I am a standards engineer, Nadeem does standards, Sendil does standards. Tomorrow, if you want to design standards, then how do I start? It's a very simple process. It's a 4-step process, whereby first stage, you collect the requirements. Say, for example, for designing 5G, somebody decided that there are going to be 3 verticals of use cases that will have to be covered. There is this enhanced mobile broadband, there is this massive MTC, and then there is going to be this URLLC. Each one of them is actually going to have a diverse set of requirements. So which market needs which requirement, collate them together. That is the first stage in standards development process. The second thing is trying to understand how should be the architecture looking like. Are we going to do everything from green slate? Or are we going to actually leverage something which is there already in the 4G, 3G world? If that is the case, then how do I actually change the whole gamut of standards evolution? That's where the architecture comes in. And then comes the detailed specification. This is what typically happens in forums like 3GPP or in IEEE or something else. But developing a specification is not the final point. You also need to develop test and certification specifications, because it needs to conform to local regulation. It needs to conform to emission requirements. Devices need to conform to how much emission which is permitted and how it can be done. There needs to be testing on the call quality, connection establishment procedures, interconnect procedures, handovers, and all these things. So test and certification is all is needed. We people were actually participating in standardization activities, which is specification writing. But now we are like benchwarmers doing mostly test and certification, architecture, requirement, and other related part. So how do I know what is standardized and what is not standardized? If this is the network you are actually deploying, where there are any different type of devices, cell sites, base stations, backhaul connected to core and to the internet, you standardize the logical architecture. You try to find out what are the protocols or the interfaces that are involved so that a base station can communicate with the device. Base station can communicate with the core, or the core can communicate with the internet. These things need to be standardized. Functionality of all these equipments in the puzzle, they have to be standardized. But you don't get into saying this is the way you have to implement it, or this is the algorithm that need to be run in there. So this is like just a few rule of thumbs based on which the standardization typically happens. And where do these happen? It happens in 3 different bodies, depending on what exactly need to be done in an evolution. So standard developing bodies like 3GPP or the IEEE, which are like global, does a lot of these specification writing. And then there are these Indian entities like the Bureau of Indian Standards, Telecom Engineering Center, and the TSDSI, which all are categorized as standards developing bodies responsible for creating specifications. Then there are regulatory bodies on which these conformance need to be held to. There is ITU, which defines and is responsible for intergovernmental or interregional conflicts and other related things. So it specifies this is your cutoff. In this particular region, this particular spectrum is used for satellite communication, so you cannot use that. Or if you're deploying it, this is the coexistence rules. So those things are specified by them. You can map it to similar things happening in the US done by the FCC, or try, they are the regulator for us in India. And then there are a lot of industry fora which actually helps promote these technologies to be adopted. So you have the GSMA, which is like a global body. We have the Global Mobile Standards Association, GSA. And then you have Indian entities like COI, who actually work with the ecosystem players in ensuring timely rollout, managing issues, and all related things. So what is the principle of standardization? Few rules. Standard is what is minimally required for a transmitter to communicate to a receiver. It can be the uplink or it can be the downlink. So those messages need to be standardized. While standardizing, you ensure that you have a life path for the device and equipment to actually move further in the evolution. So if you are designing a network today, I need to ensure that it is backward compatible to what was developed earlier, meaning today's phone should communicate with yesterday's network, and it should be also able to get into another network which will come later in the year, right? So it's telescopic both ways, backward and forward compatible. The next big thing is it needs to give a lot of flexibility, right? So if you think about Indian network, 2300 band and 2500 band are the most pioneered 4G bands, but that may not be the case in other regions of the world. So the Airtels, Jios, Vodafone of India, they need to have a flexibility to basically ask for equipment working on these bands and discard those other bands which they are not needed at all. And if you look into the other way around, Indian operators were the first ones to deploy VoLTE on a larger scale. You go to the US, you go to the Europe, earlier parts of the year, it was mostly call handover to 3G and then the call establishment in 3G, even in the LTE timeframe. Right? So there were a lot of flexibility given for these operators. The same way, network vendors and device vendors, they also get a lot of flexibility in terms of how they actually implement features. So you define the signaling messages, you define the requirement for boundary limits, and then the performance. And then everything is left for you to innovate. That is what differentiates a Samsung phone from a OnePlus device, from an Apple device, from a Lava, Micromax, or whoever it is. And that's exactly what also differentiates these vendors, Ericsson, Nokia, Huawei of the world. Okay. And 3GPP is the large body which actually standardizes a lot of these aspects. And it does this under like several different buckets. There's a group dealing with the radio access network, another dealing with core network, another dealing with services. Some define test requirements, some define how the user equipment need to look like. They all work in synergy. So what they do a large scale program management, break down parts of the problem into smaller buckets and deal them in separate groups. How does that happen? This is how it is. So a typical workflow in 3GPP happens with every single release since its establishment. It starts from a vision and a concept of a new technology. Companies then propose projects that can solve the given problem. With ecosystem consent, it then moves into study item phase where companies work together to understand and frame the problem better. The result of the study item is usually one or more work items that allow nominative work to be done. That is the normative work to be done. Once the work item is completed, the specification standard is considered complete and commercialization can happen. But remember, vision is key, which means somebody is actually working in an ecosystem scale, trying to find out what exactly need to be done. The background R&D is done. Then it gets into the 3GPP machine, comes out, and then the product differentiation actually happens. So moving into 3GPP NR design, let's see what exactly was the different generations looking like and what actually happened. Right. So as I mentioned, the first generation was the kickstart for all the mobile aspects to actually roll out. So from the AM space, we are now at LTE and today at 5G NR deployment timeframes. what was like voice all along until 3G became some amount of data in 4G, and in 5G, we are actually seeing at a unified future-proof platform. So it has done a tremendous leap over the last 10 years. So today we are deploying and evolving 5G, which builds on previous generations combined with continuous research and innovation. So what exactly is that, right? So why did we do 5G? Because it gives us the technology leap needed for new capabilities and reduced cost. That wasn't possible when 4G was defined. Between these generations, technology breakthrough, new architectures bring the technology leap, and one 4G example is hardware enablers for much faster processing. This fast processing allows us to introduce the efficient things like TDD structure, but also scalable numerology to scale 5G from low band, mid band, high band, and other things, going all the way up to millimeter wave. The hardware progress is also one component that helps us overcome the impossible challenge, connecting mobile millimeter wave, not fixed, it's mobile millimeter wave. This is all sitting on our engine of continuous research and innovation that follows by all the participants of the 3GPP ecosystem. So what exactly is this, right? So 5G NR, the way it was conceptualized and designed, it is a unified, more capable air interface. The expectation is it is supposed to serve a diverse set of services, diverse spectrum, diverse deployment, a certain industry benchmarks. It needs to improve the end-to-end latency significantly for robotic-like applications. It needs to add experience, more and more throughput. For that, you need like either larger MIMO or you have to go to higher frequency bands. A lot of these functionalities had to be added, right? So what exactly is that? Let's try to break down these three diverse things into smaller categories and see what enhancements we did there. So if you're talking about the different use cases, as I mentioned earlier, there are three. The way it was conceptualized in ITU and in elsewhere, you are targeting enhanced mobile broadband, mission critical services, and massive Internet of Things. And some of those modularized enhancement that went in there are actually listed in this in here. So you are talking about spectrum sharing, flexible slot-based frameworks, scalable OFDM, massive MIMO, and several other things for broadband enhancements. For URLLC, you are talking about use cases like drone, private networks, and all these things. And moving into massive Internet of Things, you have like things like grant-free uplink, narrow bandwidth, efficient signaling, and all those things, right? Moving into this diverse spectrum, what was the big issue or what was the big transformation that happened? You migrated from a scenario where for 4G, you were talking a maximum of 2.5 gigahertz band, which was like lower mid-band spectrum. And you're now talking about more and more capacity, which means where can I find the spectrum? You have to go all the way to the millimeter wave, right? So Sendil will actually be talking more about spectrum and how we are actually getting in there. But the catch is, right from design, it was conceptualized. It's not going to be about that lower part of the spectrum alone. They have to migrate to an upper frequency band. And then talking about the 5G vision, if you're talking about 5G deployments happening worldwide now, there are different set of use cases already happening. You have your public networks, you have private networks. There are operators who are using 5G NR technology for fixed wireless access. Some are using it for extreme broadband coverage. The same thing will be used for smart transportation and for indoor related experience. But why? Why do you need to actually have these sort of things? What is the motivation? Right. So we try to see inside Qualcomm, what exactly is the killer need to actually move away from one generation, which was 4G, to 5G, which is now today. And the study basically concluded that with 5G, if all these use cases are actually addressed, then by 2035, about $13 trillion worth of goods and services can be driven just by the 5G powered digital economy. That is a big motivation, right? Because this number is not small, right? And that's why you would have actually seen a lot of these countries promoting the use and adoption of technology in ensuring that these transformation from 4G to 5G NR based thing happens sooner than later, right? And that's precisely the reason why in the 5th generation NR network was deployed even before ITU actually standardized that and recognized it. Right, so that push has already happened, and you will also start seeing this push happening in India, like in the next 6 months, or at best by 2021 timeframe itself. So what exactly is 3GPP NR and what was its basics, right? So let's look into the design guidelines. And this guidelines, when it was framed all the way back in like April 2016, or second quarter of 2016 calendar year. Few thumb rules. Yes, there are going to be two different things that are going to be big. We are going away from a LTE waveform to a new physical layer design. That was agreed. And then the second big thing was you are actually going into a service-based architecture, trying to see how more and more digital services can be pushed in this network. So what changed? It will have to exploit high frequency band to obtain additional spectrum. It has to be ultra lean design, meaning it has to be flexible enough to actually accommodate the huge EMBB use case, and it should be also thin enough to accommodate the narrowband IoT or URL select use cases. It has to coexist with LTE, and it should interwork with LTE. It should be forward compatible for new use cases and services that will come. Right from conceptualization, ensure that low latency and high reliability and power saving are like fundamental things for this design. And the big thing, it's a beam-centric design. So it's not about just link budget and other things, but the link budget is influenced by how you form your beams, how many beams are being formed, and how do you actually leverage those beam-based designs. And some things actually changed. There was a waveform, the cyclic prefix-based OFDM with scalable numerology was fundamental to it. It also had the DFT spread OFDM waveform with uplink for coverage. You're also bringing about new channel coding things like LDPC codes and polar codes. And in terms of reference signals, the break from LTE to NR was don't transmit your controlled signals all the time. You just transmit it when it is needed. So that ensured that you're actually going into sleep for a very, very long time as needed, right? So what are the technology components that got into it, right? So we are just listing a few of these things which actually came during our interactions to be very important. First thing is the scalable OFDM numerology. I'll explain that in exactly 2 slides on what I mean by scalable OFDM numerology. Self-contained structure, same thing, 2 slides. The next big thing was LDPC and polar codes. This actually turned away from the turbo codes, which is actually employed for LTE. So what flexibility it gave? It actually gave better rate performance. And it also ensured that I can actually vary or adapt my payload differently for different services. Okay. And then we also discussed about massive MIMO and mobile millimeter wave being the main use cases for 5G or the main enablers for 5G. So fundamental, 5G will utilize the OFDM based waveform that can be adopted for scaling to an extreme variation of 5G requirement. This legacy is carrying forward from LTE because it works, and then if you are talking about very, very large bandwidth, then that's the waveform that you'll have to use. It's suitable because of the following reasons. It can offer high spectral efficiency, meaning it allows low complexity MIMO implementations that can add more streams easily and then get closer to the Shannon limit more effectively. It's also flexible for lower complexity because it reduces the complexity at the receiver, right? You're talking about the mobile device, and we all know mobile device, it also does communication. So you also use it for speaking. The other purpose is that's where the battery gets drained or used to. So your Facebook, WhatsApp, Signal, whatever you're talking about, that's where majority of the time it's used. So you have to ensure that you're effectively using power resources for your communication module, right? So that's the key. Good frequency localization, like additional OFDM windowing. So based on which region you are and how much stricter use of filters need to be used, this was flexible enough. Low power consumption and better asynchronous multiplexing, allowing for varied optimized waveforms and multiple access schemes to coexist. Example, support for asynchronous grant-free transmission for IoT and other things. So let's look into the next 3 slides in a little bit of detail. So what exactly changed from LTE to NR in terms of the waveform? So as we know, LTE waveform, the most of the implementation as of today supports a single subcarrier spacing, which is 15 kilohertz. What was the catch to it? When you're now talking about large cells being deployed for the way we are doing today, like urban cells and other things, logically spaced at given distances, it works perfectly fine because it's like similar setups being replicated at every base station. But then NR wasn't designed to do that way alone. You're talking about low frequency and you're also talking about millimeter wave frequency. So trying to have the same subcarrier spacing for millimeter frequency is not going to be like easy. Why? Because you're talking about 20 megahertz or at max 100 megahertz, say in the 3.5 gigahertz band. But way up in the millimeter wave band, you're talking about gigahertz and gigahertz worth of spectrum. So if you're talking about very, very narrow chunks, the system design is going to be complicated. So you are talking about very large chunks in the frequency domain in the millimeter wave. So NR design actually allows for that flexibility, right? And what is the first rule of thumb we had? The time of the signal is inversely proportional to the frequency. So if the frequency increases, then the time is actually going to shrink, which means you're actually going to have more and more smaller samples in the millimeter wave space, right? So NR basically supports a multiple of 2 power n subcarrier spacing in multiples of 12. So if it is an outdoor macro coverage, say like in the FTD deployments in 700 megahertz band, you can use your 15 kilohertz subcarrier spacing. Or if you're actually going into 3 to 5, 3.5 gigahertz deployment or whatever, then you try to use 30 kilohertz subcarrier spacing. And this is like flexible enough to deploy up to 100 megahertz bands. You're talking about indoor, go probably for a 60 kilohertz subcarrier. Or if you're talking about millimeter wave, deploy it with the 120 kilohertz subcarrier spacing. Right? So effectively address 5G diverse spectrum deployments and services using this different numerology. So how does the OFDM grid actually look like when you're actually talking about NR deployment? Right? So this is how it looks like. So you're talking about a lot of these time frequency grids. And what is the usefulness of this is you can actually now partition the grid into several different regions where different services can be deployed. So I have just given an image of a flexible slot-based framework. In release 15 of the specification, the main purpose was to complete EMBB use case. It also addressed things like dynamic spectrum sharing and but also wide area mission critical things to puncturing. What do I mean by that? If you're talking about a URLLC like use cases, like say for example a patient monitoring system, you can't wait for a network to give you a grant before escalating to the network that this guy is getting a heart attack. So the moment the sensor actually senses something, it will have to push it, not wait for a grant. So if you're pushing it and if there is another transmission happening at the same time, how do you ensure that there is no collision? Or how do you notify the network that a URLC packet is coming? And how do you ensure that error-free detection of that packet is still feasible? That is what was fundamental to picking up those particular schemes when this particular time frequency grid was actually done. And then when you go into release 16, there was like additional services that need to be added, like cellular V2X or broadcast like ENTV or other things, or trying to ensure that narrowband IoT, which was done in the LTE world, can actually coexist with this. Moving further in release 17, there were a lot of other things like sidelink, NR Lite, and several other things that were actually added into this particular framework. So we saw frequency, we saw the time frequency grid, and how does it actually look in the time domain? So in the time domain, there were like few options that were actually provided. So if you're in the conventional 15 kilohertz subcarrier spacing thing, then you look very much like the LTE waveform. So now we can actually coexist in there. Can I also coexist if I'm using 30 kilohertz, 60 kilohertz, and 120 kilohertz? Yes. So if you need to do that, then you need to ensure that those parameters are appropriately chosen, and then you do something. It also supported the notion of a mini slot, a self-contained slot in which actually you can actually send your control, feedback, and all other related things. And a lot of these functionalities actually came. Moving quickly into URLLC, the main purpose was in actually ensuring things like robotics, automation, remote medicine, smart grids, all these things can be done. And I threw in actually a lot of these jargons. But if you look into all these use cases, they have very diverse purposes. Robotics, the key thing is precision. Remote medicine, the key thing is you should be able to send messages instantly. Autonomous vehicle, The challenge is you may have to work when there is no network presence at all, meaning device to device like mode. Drones and other related things, it's a very good use case. But the problem is all these towers are actually facing towards the ground, and this guy is actually flying in the air. So how do you actually communicate with those things? Industrial automation, the biggest challenge. It is not concrete, it's not windows, doors, wood and other things like your home or in your office or in your living space. It's metal, metal, metal everywhere. And you know how bad signals actually perform in terms of all these reflections, scattering and other related things. Smart grid, however good we may like it, the challenge is for a country like India, you have to have at least like you're talking about 1.4 billion people today, which is like 300, 400 million households, and then equivalently 100 or 200 million industry places. All these things will have to be actually given an energy meter. They will have to be actually connected to a grid. All this information are going. Very small payload, but huge number of devices which are actually communicating in an erratic fashion. So the network need to actually be managing all these aspects, right? So instead of actually doing FDM like things, mission critical services, setting aside spectrum capacity for mission critical, that would be wasteful. So how do you actually leverage all these things? As I mentioned, one of the main things we want to probably do is actually sending the payload as and when it becomes available. And that means you need to get into new modes of error correction codes that will be needed, because you're actually communicating when somebody else is transmitting, and hard designed payloads and other related things for that. Delivering links with low latency and increased reliability does not come without any trade-offs. So depending on how you are actually matching it, are you going for latency optimization or capacity optimization? The NR actually offers a lot of flexibility, and same way with reliability, capacity, and other related things. I'm actually rushing it a little bit because I realize I'm 10 minutes late to hand it over to Sendil. So I think 2 slides and then he should be up. So 5G NR, how does it work on NR IoT to fully leverage the LTE IoT evolution? The time frequency grid, as I mentioned earlier, it's flexible enough to ensure that a small chunk of time or a small chunk of frequency can be allocated for these particular use cases. And the way it was designed, it basically told narrowband IoT can exist with me, and then as and when NR changes into NR Lite or something for future evolution of NR, it will be able to scale to those new use cases. The last thing in session 1, it's about mobilizing millimeter wave with 5G NR technologies. The whole idea is deploying a dense millimeter wave network with spatial reuse. So I'll be explaining in like the third session that how LTE and NR will have to coexist. But the key thing is you are actually integrating with several different deployment options in your network, including use of millimeter wave for diverse antenna and dual connectivity and other related options. Okay. With that, I'm actually concluding session 1. And Sendil, can you take up for session 2 on spectrum and other things? Sendil?
Hello. Yeah, I'm audible now?
You are audible now. I'm stopping to share and then you can take it.
Okay. Let me know if you get to see the screen.
I can see.
Okay. Okay. Are you able to see the full screen or present of you?
The full screen.
Okay, good. Thanks. Good. Thanks, Vinosh. Maybe we'll start with the session 2, where we will actually start looking at what exactly was new from the 5G perspective in the context of spectrum. Because we have been adding more and more enhancements to LTE, 4G, adding capacity. But there was time when there was a need which says, okay, now we need to build a technology which can actually get into millimeter wave bands. and millimeter wave band is widely used in satellites and other services, or even in microwave backhauls. So that was one key part, and then that needed to see that what are new things that is to be done within the standard developments. So we'll focus on that. So the moment we talk about spectrum, this is not something which is very country specific or region specific. This is something which very sensitive, and it has to be. It's more of a policy matter. So today, if you look at the spectrum globally, has been under a body from ITUR, which manages radio regulations. Spectrum has been primarily used by satellite, marine communications, radars, and a lot of other services. So it was very important for a global body to see that how a spectrum is going to be used. For example, say a ship leaves from the land water boundary from India and then goes to the neighboring countries, right? And then the ship uses a particular frequency to talk to the terminal on the land. And then the moment they go into the little bit beyond a certain sea and then sea boundary, suddenly if the same frequency is being used for some other purpose, they're going to be there is a loss in the communication, right? So there was a need that, especially spectrum which is used for safety of life, especially on land, sea, or even flying aircrafts. So it was necessary to ensure that there is a way where all countries agree that we are going to use this spectrum for a specific kind of services. That's the broad theme why ITUR comes into picture, and then they bring all the countries together and say, basically there's a conference that happens every once in 4 years, and then they try to find out for what services, what spectrum is being used, is there some new need needed, right? So they keep updating the radio regulations. And mobile services, not just the normal phone that we are looking, mobile services typically termed as any communication that happens on a radio where the transmitter or the receiver or both of them are moving. Either they are on one of them is fixed on a terrestrial, the other one is moving on the sky, right? So that's how it get categorized into mobile services. Since the time around 2G and AMPS, mobile or cellular industry has actually impacted most of the countries, and they had a need that we all need to move from one country, or when you're roaming from one country to another, we don't have to handle different phones, or else there will be an issue saying, for example, if some frequency is meant for a mobile phone in, say, in Japan, and the same frequency is used for some other purpose in another country, then a phone like today, which we are freely able to roam in globally, you would see that you'll have to have different phones for different countries, or different models, or different RF chains for different frequency it is being used. So the countries came together and they understood that there is a very important aspect that we need to focus and to find out a chunk of spectrum that we can identify specifically for IMT application, that is international mobile telecommunication. And they said, okay, we all countries will agree that this is a spectrum portion that we want to identify for IMT. And then the benefit of this is that when a product is made, say for example, all the countries decide that today we are going to use the spectrum for IMT in the next 4 years or 5 years, then the entire industry will actually be able to build chipsets and products, even the standards, everything will work so that it can be scaled. One device that is made today can work globally in different countries. So that was the background behind having a spectrum identified for IMT globally. This is what typically called as globally harmonized spectrum. So this is where IMT applications are put. Now, then the next question comes in that, okay, what if some country says you are making a technology which is I'm going to identify for IMT, but that application is only doing something which is necessary for your country, may not be applicable for the other countries, right? So then the next step that was brought up is saying, okay, how do we identify what is the IMT system? So ITUR set up requirements and vision saying these are what we see that as a technology like IMT 2000, which was published in 2000 in the year 2000, that says any wireless systems or radio technology that can meet these requirements will be called as an IMT 2000 system, and then that system can be deployed in an IMT band. So this is how the need of defining IMT and the technical characteristics, what are the requirements, that comes into important role in this ITUR spectrum perspective. So if you look at on the slide, what you see is there are, if you look at IMT 2000, they started drafting a vision that what we call as an IMT 2000 system around 1992, and it just and the time it got published, it is 2000. So it's about more than 8 years it took from the vision to a standard or a technology to be called as an IMT system or IMT 2000 system. Whereas if you look at IMT 2020, which is the 5G system today, it just took 5 years, and especially 2015, the vision was published, and in 5 years there is a recommendation in 2020 saying these are the technologies that we call as IMT 2020 system. And 3GPP has been part of the recommendation in IMT 2000, IMT Advanced, and IMT 2020, LTE and 3G, LTE and NR in this. And one important part that we need to take away is that compared to the previous generation of 3G and 4G, you might be surprised to see that I'm saying that ITU just recommended 3GPP NR as IMT 2020 in just this year, right? But then we have already been seeing deployments and trials happening all the way from 2018 itself. There has been trial which says this is a 3GPP spec, and then this is how it performs. So basically, we are seeing that industry and the technology recommendations are actually chasing each other. And why millimeter wave band? So when IMT 2020 specifications or the vision was set, like what Vinosh mentioned in the earlier slide, that one of the vision was saying 5G is a generation of technology that has to be used in multiple ways other than just mobile broadband. So that vision document included saying, yes, this IMT 2020 technology will also be able to operate in millimeter wave band, and that become an essential requirement in the IMT 2020. If you look at the requirement that is set in IMT 2020, is saying typically millimeter wave bands when used in indoor or dense urban, there is a requirement to show what is the capability of that technology when operating at 30 gigahertz range. So that's a representative number. And then there's a requirement that when you're operating a millimeter wave band, at least 1 gigahertz of spectrum or a channel bandwidth should be able to, the technology should be able to support. So that becomes very important. And then, like I said, every 4 years, there is a conference that happens where the technology, the spectrum has been, will be identified. Now, it's not that once in 4 years, all the countries come together in a room and then they say, okay, spectrum available for IMT. Now, the spectrum is being used by different services already. So before making a spectrum identified for IMT, there was 3GPP had started developing saying this is how the channel model look like in millimeter wave band when I'm using a phone and a base station talking to in millimeter wave band. 3GPP also had to develop saying when you radiate something in using the 3GPP NR specification, this is how the spectrum mask will look like. These are how the capabilities we are going to leverage like an active antenna systems. These inputs went into WRC. Based on that study, that it was decided, yes, an IMT, NR in millimeter wave band and other services can also coexist. They can operate without interfering with each other. That was one important aspect that helped to make that decision. So, so in addition to making 3GPP, specifications of NR frame structures and other radio characters, it's also important to see that how the spectrum is secured and can be used to operate without interfering other services. So globally today, if you see, ITU has recommended or identified 26 gigahertz, 40 gigahertz, and 66 gigahertz band for deploying IMT 2020, where it has been identified. But then it also comes with new conditions, which says that if you're operating, for example, today we see a lot of weather satellites which says how much of cloud is there on, or there is a possibility of rain. Right? So there are weather satellites which actually sense the water vapor in the cloud. So these are passive sensors. So when the satellites are moving and collecting the sensing, the passive sensors are sensing these values, they also see that those sensors should not be interfered. So some of the outcome that came up during the WRC is saying that any radiation that happens in 26 gigahertz band should not interfere or limit its emission in this portion where the passive sensors are operating. So if you look at, there is a restriction of minus 33 dBW per 200 megahertz for base stations if they are launched before September 2027. And if it is used after 2027, it is minus 39. It's more even stringent, 6 dB more stringent. What does this mean? This means that if you're building a product, your out of band emission or a filter should be more stringent beyond this in this portion of the band, 23.6 to 24. Right. So these are new things that actually had to get into the 3GPP specifications, because if you're not adhering to these specifications, you're not allowed to radiate. Okay. So these are additional restrictions or regulatory condition that has been added, which is very important to know. And now I'll skip to 3GPP bands. So in addition to ITU recommending or identifying band for IMT, uh, there are other sources which also says that we are looking to deploy IMT or 3GPP in so and so bands. Countries like UK, South Korea, Japan, Canada, Australia, they had already had intentions or assigned spectrum, saying this is a spectrum where we think we want to put millimeter wave band for services like fixed wireless access. So the operators from those countries actually brought in contributions to 3GPP and said, we want to develop radio which can also operate in 28 gigahertz band. So if you look at 28 gigahertz band, did not wait for WRC. It's a band which is being already commercialized and networks are deployed. Right. And the reason why we are looking into millimeter wave band was one reason what Vinosh had brought up, saying large spectrum chunk that's are available in the millimeter wave band compared to what we have today in the sub gigahertz band or the mid bands. So when 3GP started designing the specifications for millimeter wave band, there are other challenges that comes with it, right? So the key part, the one of the important one is the propagation loss, propagation characters that comes with millimeter wave band. There is a diffraction component. There is an outdoor to indoor penetration which is much higher compared to mid band or low band systems. Then the millimeter wave bands are also very sensible to rain or atmospheric attenuation. It also depends on how much of rain is happening. It also depends on the snowfall, whether it is a wet snowfall or it is a dry snowfall that's happening. And then body loss. When you're using a phone next to your ears, it may add additional 1 or 2 dBs of loss. So when designing system, it also needs to know that when a control channel or a uplink channel is being designed, we need to ensure that all these propagation losses need to be compensated or included when calculating the range of the cell. Then in addition to that, radio regulations. So just mentioned that WRC had different new radio regulation that has brought up. So 3GPP had to include those radio regulations. How do I ensure that what is the emission happening from a radio? So in millimeter wave bands, we have out of band over the air measurement that happens. So which says that, okay, if there are multiple beams, this is the total power being radiated. So that test and methodology was also included in the specifications. In addition to that, there are other aspects like implementation aspects. For example, phase noises that happens in the millimeter wave band. So the specification had to include necessary signaling mechanisms to address and measure that. Right. So the key components that started when we started working for 3GPP in millimeter bands were starting from the channel model. So in release 14, 38901 basically has the channel model which includes 2D channel models and which includes the ability to see vertical and horizontal directions, which includes the channel model all the way numerology. If you look at to support millimeter wave bands, higher subcarrier spacing of 60 kilohertz to 120 kilohertz are added, which allows to have small CP durations. Look at the CP duration, the symbol duration has gone down all the way till 9 microseconds and CP duration of 0.59 microseconds. This basically says that you cannot have a delay, multipath delay that's coming up beyond 0.59 microseconds. Basically, you are restricting the multipath spread. Right? And given that you also have a higher carrier frequency, your Doppler shift also increases. The Doppler shift can go all the way till 18 kilohertz compared to what you have for the mid-band frequencies. So you need to also accommodate that. Right? the base station may be able to transmit all the way till 400 megahertz of channel, but then whether the UE need to also keep its radio front end open for the entire 400 megahertz, it is going to be a challenge in opening that. So there is additional feature which allows that even though the network may operate at a wider bandwidth, the UEs can still operate at smaller bandwidth parts. So the base station can say, I think I have a slide later on that. So we'll get into that later. And then there are path loss component that need to be addressed, basically to include active antenna systems, new OTA measurements, over-the-air measurements of base stations which are specifically operating with AAS systems. WRC 19 regulations had to be brought in. Right? Now, since we already started working with millimeter wave bands, there are new things that got attention into the specifications. Non-terrestrial networks, basically all the satellites, LEO satellites. Now, if millimeter wave band is already being used by VSAT terminals talking to satellite, why not use the 3GPP NR also talk to satellites? So those are new study item that is happening, and probably 3GPP NR will also support connecting satellites through NR. Right? So there is an existing study report that 38811 you might be able to have a look. It has a lot of interesting research areas. And then next is integrated access backhaul. We have already been using microwave backhaul like E-band and other 12 gigahertz backhauls. So these are point-to-point links which is used to connect backhaul to the cell sites. So given large amount of spectrum like 400 megahertz or 800 megahertz that you're going to use for access, you could also use it for doing backhaul at the same time when you're doing access. So integrated access backhaul is another active work within 3GPP, which is specifically within the millimeter wave band area. So what are the key issues, right? When we see a millimeter wave band, you'll see there is a line of sight components and there are multipath components coming from other reflections around the device, right? So this will look like there is a lot of multipath and could have higher ranks, but then it is also possible that if you're having a narrow beams, all those multipath are not going to follow within your beam width. So it may turn out that these, even though there are multipath, it may look like a narrow LOS component. But within an LOS component, if these are transmitted through active antenna elements which are dual polarized, horizontal, vertical, you can see that these can be treated as two layers. So even with the beam and looking like an LOS system, you'll be able to see two layer of links. Right? I think this is the same thing, but it basically talks about having a larger beams and higher path loss. What does it lead to? When you have larger path loss, basically you're saying the coverage is going to be small, right? So small cell. So what happens is when your coverage is small, you'll be able to ensure that the entire capacity can be loaded into a smaller cells. Basically, you'll be able to get very high peak rates, high density small cells can be deployed. And it also is also reason because, like I said in the previous WRC regulations output, which says there are limits at which the power can be transmitted. So power regulations can also lead to a condition saying why it is becoming more suitable for small cells. CP overhead. Because of higher subcarrier spacing, your CP duration is less. Basically, you will not be able to cover larger propagation delays. Right? This is a small snapshot which I had put up. For example, when do you decide what subcarrier spacing should be used? Maybe I'll try to skip in the interest of time. Right? Yeah. So the important component that we see when you talk about millimeter wave bands is active antenna arrays or massive MIMO. So what it means is when you're talking about millimeter wave band, your lambda is small. When you say lambda is small, you'll be able to place antenna elements very close to each other. And with a smaller antenna size, you'll be able to pack more and more antenna elements. Today, we can have almost like 128 antenna elements within a smaller panel. So which allows you to pack these antenna elements together and form beams. If you look at this diagram, if there are high-rise buildings, you could, the way you combine these small sub-arrays will say that how these beams are looking like. If you have a smaller sub-array with just only one sub-array, it could have a wider beams. And if you try to combine multiple sub-arrays vertically, you will be able to make smaller beams, which is a smaller vertical beam width. Right? So based on the deployment conditions, and where it is deployed surrounding nature, you'll be able to use or design the beams accordingly. So if you're using the same antenna array for a rural environment where you're looking for a larger direction, you would want to look for uh, a larger coverage area. Your vertical beam width need not to be very small. Right? So flexibility of using specific design. The other part which I was bringing up is the phase noise. So during the release 14, since NR has to be the path loss component, and in addition to the path loss, when there is a Doppler shift because of millimeter, look at this 28 gigahertz, there is the Doppler shift is around 18 kilohertz. So if you have to accommodate that, it means that even a small shift at that carrier frequency can lead to several dBs of phase noises. So I think this particular block shows around, if you're operating at 28 gigahertz radio, you can see that with the 18 kilohertz Doppler shift, there is a phase noise around minus 90 dBs C per hertz. So it is important that the base station and the UE device need to keep tuning the phase, need to track the phases between the transmitter and the receiver side so that they can reduce the phase noise. So this has introduced phase tracking reference symbol which has to be transmitted, and I think it has multiple densities at which you need to transmit. And so based on that base station, this is done at both sides, the downlink as well as the uplink side. The other part which I just mentioned earlier was the bandwidth part. When you have larger bandwidth, so this is an example where you can see that even if you have 400 megahertz of a carrier bandwidth, a UE can say that it may not be able to support the entire bandwidth. So UE can inform network that I can only support at a time 100 megahertz at a time. So a particular bandwidth part can be assigned to the UE 400. Or it is also possible that if the 5G device is used for a factory or maybe attached to a machine, it is possible that it might have a broadband pipe that is needed to send high data rate, as well as it might be requiring a very low latency application that is happening at which we need only a smaller bandwidth that is needed. So a base station can actually assign or configure multiple bandwidth parts and say that at any time you're going to now switch to this particular bandwidth part. Either it could be a larger bandwidth, it could be a smaller bandwidth, and it can keep switching between them. So I think I did cover about this. So as an example how you have a 64T, 64R antenna where you have a dual polarized antenna elements, horizontal and vertically polarized, and then you have a sub array which is 2TX, 2RX. Right? And then when you combine these, you arrange these multiple sub arrays together. Now from a UE perspective, it is completely transparent how these sub arrays are added up. So either the network may use these two sub arrays together and form a beam, or it may use combine the vertically all the sub arrays together and form a vertically narrow beam. Right. So from the UE perspective, it does not need to know how it is done. It only needs to say that how many ports are available. It just sees that okay, if there are 64 ports, it just sees I'm seeing a beam, I'm seeing at this port, and this is where I need to transmit. So it does not know how this combination is done. The other way is so this gives a flexibility of site-specific implementation. A site where we see that okay, there are not vertical buildings, I could have a wider beams so that I don't have to do any vertical switching. And if there are users, if I could separate between in the vertical directions or in horizontal directions, it could also be used to minimize the interference into adjacent cells. Or, for example, we could avoid creating any beams towards a certain directions where we don't have any users in that. So it is possible to do beam steering. So I think digital beamforming is something which is known, been there for from LTE days. Where this is an example which says that if you are using a smaller mid-band kind of applications or a 50 megahertz system, the way users are multiplexed are in the frequency domain. User 1 and user 2, you see that on the vertical side is the layers. The red UE2 is scheduled with 2 layers because with a rank 2, whereas the user 1 is being scheduled across 2 slots but with only rank 1. And then if the UEs are in very good situation or an SNR region, when multiple users can be scheduled at the same time. Right? So This is the MIMO with one layer for each of the users. When we go to analog beamforming, what happens is typically when we are using analog beamforming in a millimeter wave band, you have a large spectrum available or a capacity available. You're not very keen on saying do frequency domain multiplexing. Instead, what we do is we create a beam towards one user, and we know that the duration of subframe is very small compared to a midband carrier, right? So you could actually use the entire band for one user, switch the beam, and then schedule the other user. So basically, the entire spectrum or bandwidth can be scheduled in a beam towards one user. So it's more or less more like a time switching or beam switching across users. Now, if you are going to switch users like this, then there is important that how do we communicate the common information or a system information. So unlike LTE, where there was a specific location at which continuously or periodically we have this SSB synchronization signals were transmitted, whereas in NR it allows you to transmit less periodically. The network can decide that, okay, if for example in a factory environment or in an industrial environment where we see that there is not much of a mobility happening, right? It could actually reduce the periodicity at which SSB blocks are being transmitted. And especially for millimeter wave band where the duration of the symbols are very less, you could transmit all the way up to 64 SSB blocks in time. So it becomes easier to search and attach to the network. Now, how do we efficiently transmit SSB blocks so that when I turn on, I need to find the common broadcast information from the network. Either the SSB can be transmitted in a beam which is having a wider coverage like this, the green one, and then when a user is attached, and then you have narrow beams on which the data is scheduled. This is one approach. Or you could also have multiple beams, and then this SSB block is scheduled in each of this beam, and the beam keeps switching. So that when the mobile is turned on, mobile also might have multiple beams. It keeps scanning for all possible beams and finds that I am able to connect to the system. Right? So there are multiple ways to implement or transmit the SSB blocks, and it's completely up to the implementation side. From the standard side, it does not say this is exactly how they are deployed. So this gives more flexibility based on the site location that you're looking at. Let's see from a, how am I keeping with time, Vinosh, for your session?
You're okay.
Yeah. So let's say if you are looking from a base station side, if I'm sitting on the radio on the site, and then if I'm having a active antenna set up on it, and then if there is a small vertical beam width, right? And then if you look at this basically sees all the users all the way from the cell edge all the way to the mid of the cell. They are in the same beam, right? So in that case, you'll see that you would want to actually switch across horizontally so that you'll be able to pick users in different directions across the cell. So this is how you will actually see the users. And using the same number of antenna elements, if you configure it, this one says basically there are all the sub arrays in the vertical directions are combined together, which forms a very narrow vertical beam. Whereas you keep on switching in the horizontal direction, the horizontal beam width is higher. Right? Now, if you look into the same urban scenario where you want to have vertically switch users, now you see that you can actually have more number of beams and pick users in both the directions, the 2D directions, vertical as well as the horizontal. So this gives more user separation as well as higher bandwidth to the user in that particular beam. Yeah, so before I switch, so then we will see that now we've seen all the basic components of AS, phase noise and everything. Then we'll see that how do we actually plan or see that what is the typical capacity that has to be estimated. I think we'll continue in the next session. Is that okay, Vinosh?
Yeah, that's fine.
Okay, good.
Can you unshare so that I can share?
Yes.
Okay.
Nothing, do you, let us know if you think we need to plan a break or something. It's almost like 1 hour we started. Vinosh.
Yeah, there is a question posted in there. Maybe you can just take that and then we can take a break. Uh, there has been a lot of research focusing on non-orthogonal multiple access NOMA for 5G instead of OFDM. Can you highlight in the context of 3GPP if it all includes mentions NOMA? So I answered that, but I'm not very comfortable with the system. So it's appearing as it's a separate question. So NOMA is still work in progress in 3GPP. Even in release 17, it is being considered. There are like a few practical aspects that need to be resolved. So I think the proponents, mainly coming from CATT and other entities, they are still pursuing that path. It's not discarded yet. It's still in the table, but it's not standardized yet. That's the current situation of NOMA. Sendil, maybe you need to take the second question. We haven't heard about 47 gigahertz deployment yet, though 28, 39 gigahertz deployments are ongoing. Is there any challenges for these type of deployments?
I think, okay, maybe I'm surprised. Why did that not come up? I have a slide which talks about typical deployment that has happened in the millimeter wave band. Okay. Let me just show this one. So in US, there are deployments happening in 39 gigahertz and 43 gigahertz. Some of them have been licensed, and I think
Sendil, you're not sharing.
okay. Yeah, I don't have the 29 gigahertz thing. Okay. Yeah, so I think it depends on. Am I audible? Okay.
You're audible.
Yeah. So basically, I think the reason why which band is prioritized, or it also happens that it's not very immediate that some it gets identified in a WRC for IMT and then it gets immediately implemented in a country. So there are a lot of national process that happens because the government also need to see that the existing users are available. The spectrum is widely available for a non-fragmented way. So those national activities will happen before it gets into the state where the governments or FCC, for example, would say there's a band we are going to release it. That band is also being used by other satellite services. So they'll have to see there is a sufficient chunk available before it is made for 5G.
Just to follow up with what Sendil mentioned, that band is available, but I think the priority is in the 26 and 28 gigahertz band, and maybe probably next in the 39. So once all the spectrum is exhausted, then you'll see a large scale deployments happening in 47 gigahertz. So there are like very, very small scale deployments happening today, not the way the millimeter wave of 26 and 28 are currently happening. That's why you're not hearing about it. But the harmonization effort is completed and the progress are taking place. There is a new question that popped up. So initial deployment of 5G will be based on dual connectivity, where UE can get connected to both LTE cell and NR cell. Will it be more power hungry? Okay. So my next session is supposed to be focusing on this question first. So we'll answer your question in there. Is that okay, Gessen? Okay. So that's where the questions are. Maybe we can take like a 5-minute break. And in the chat, I had actually posted one question for you, which basically says, if you had to design a millimeter wave support in a handset, what's the best option you are going to look for in a scheduling grant? Is it going to be narrow in frequency? Is it going to be narrow in time? Or, it doesn't matter. So basically, post your response with a justification, and let's see how you are thinking about this particular question. Okay. So it's 6:17 in my clock. We will wait until 6:21 my time. And then at 6:22, I will start session 3. So 4 minutes break. Sendil, can you confirm if you're able to see my screen?
Yeah, I can see.
Okay, thank you. Okay, let's get started with session 3, where we will discuss some of the deployment options first, and then explain how NR deployments are expected to be planned and deployed. So, yeah. So I think rule number 1, LTE advancements are going to be essential for 5G NR deployments, right? So we are not going, we are not expecting NR deployments to happen in a greenfield manner, the way, say, for example, Reliance Jio or somebody did in the NR timeframe. It's going to be one of the existing operators who will have to do NR, and then they are not going to do pan India day one. They are most likely to do it in selective places like hotspot deployments, ensuring that some of the bigger cities like Delhi, Mumbai, Bangalore, or these places where you are expected to have quick 5G subscribers getting into the market, or targeting very different use cases like industrial IoT applications, like V2X applications, or dedicated IoT like applications. Trying to focus on drone communications. Some specific areas of these deployments are going to be happening. Like if I may use the word pocketed deployments or regional deployments of that manner. So for that to happen, you are going to have a coverage band which will ensure that you are connected to it. And that connectivity today is offered by LTE. And all the 3 operators who have deployed it in India have a resilient LTE network which is already live and commercial, and they are able to have identify some capacity which can be offloaded for control channel in these deployments. So as you see in this particular figure, it's going to be multi-tiered, where so in the larger coverage region where call has to be established, connection has to happen, that is going to be provided by your ubiquitous LTE network. So voice over LTE is going to be your initial voice option in the new NR network also. You may do a switchback, or then you'll do whatever that is needed in there. And then there are going to be some new connections that are coming in with new use cases like millimeter wave hotspots and other things which will be NR based. So that's what I have actually shown in the center of this universe in there, right? So key thing, LTE is going to be critical. There's going to be a mix of LTE and NR deployments that will happen on day one, and slowly it will actually migrate into NR only systems as the evolution actually catches up. So rule number 2, spectrum aggregation is essential for our 5G NR deployments. What do I mean by that? There are like multiple options that will be again available with the operator. So if an operator has dual connectivity, meaning LTE and NR in the system, that is going to be the natural option for them. This fully leverages the LTE investments into coverage through the non-standalone mode, which comes in next slide. As you migrate, then you are getting away from dual connectivity and then starting to do what is called as carrier aggregation through multiple bands. This is going to be like the similar looking band FTD in the beginning, but as and when the network progresses, more evolution happens. You can do cross carrier aggregation between FTD and TTD bands. And then you can also subsequently do across different types, as in sub-6 and millimeter wave, or in terms of licensed and unlicensed band. So it's going to leverage a lot of these functionalities that is actually coming from the LTE world itself. So I spoke about dual connectivity. So what exactly is dual connectivity and why do we actually need it? As I mentioned, operators are going to start deploying LTE in their network. This is going to be a gradual process, and as the process continues, you will see some networks which will be LTE based, and some other networks which are going to be NR based. But the same handset is going to roam into these two networks, and it should be able to function seamlessly. It will be in the ubiquitous LTE coverage where you have several deployments currently happening, and you will get the gigabit LTE and VoLTE coverage. As and when you get into a 5G zone, you get gigabit LTE with VoLTE for your voice and other related things. You can actually have 5G NR below 10 gigahertz and above 10 gigahertz. And as and when you actually roam into a 5G millimeter wave zone, you get the gigabit downlink speeds and uplink speeds that NR promises about. There was a question in the previous session, on how does NSA compare in terms of power performance. The way to understand and answer that question is the following. What would have naturally happened if you are connected to two carriers at the same time? You are going to actually pump more power into those things. So if you are doing carrier aggregation 2 bands, you are going to be active on those 2 bands, and you are going to actually spend power on those 2 bands. So dual connectivity is no different from that particular perspective. But the right answer to that, in my view, is dual connectivity is going to be slightly costlier in terms of power when compared to carrier aggregation, mainly because of the weakness in the LTE system. The downlink control channel is always on. So if your mobile design is inherently tapped to latch onto the network and always stay on and not going into the power save mode, then you're probably going to spend a little more power in the dual connectivity mode than in the carrier aggregation mode. Okay, so hope that answers your question. And then there is going to be a different level of options that are going to be coming in. So you're going to be talking about carrier aggregation between millimeter wave, mid band, low band, across time and across options. So we are going to discuss non-standalone and standalone in like 2 slides from now. But before going into non-standalone and standalone, there's a crucial thing to be understood. And the crucial thing is that it was not a radio-only evolution. There was also a core that was changed, or a new core that come in as part of NR or 5G standardization from 3GPP. That next generation core, or NGC, is part and parcel of the Release 15 framework. And depending on which particular operator prioritized on that particular aspect, it actually got into the standard first or later. So the new flexible 5G network will deliver uncompromised performance and efficiency, leveraging virtualized network functions to create optimized network slices for a wide variety of services hosted on the same physical network. Each network slice can be configured independently to provide end-to-end connectivity that is optimized for the application's need. And this is especially beneficial for things like IoT, as its diverse set of requirements can dictate very different service level agreements, or SLAs, for the different use cases supported by the same network deployment. In addition to allowing more efficient resource allocation and utilization, the enhanced 5G network also enables flexible subscription models and dynamic creation or control of services. So what exactly is the network evolution path in here, right? So the operator gets to choose how to introduce 5G in a network. If you have an existing 5G NR deployment, LTE deployment, and then you are planning to introduce 5G NR into the system, which means you have to bring in like a new core, that's possible. So what's happening in here is what is called as option 2. You can actually roam from one network which is purely LTE based to another which is connected to your EPC core, and another network which is entirely NR based connected to the new 5G core. This handover is possible. And in option 2, what's happening is the data and control from the UE is actually directed through the NR RAN to the 5G core. Or you can do option 3, which is called dual connectivity, where you don't have the 5G core, which is the 5GC. Instead, you have only introduced the 5G radio. This is like having a few hotspots with millimeter wave deployments and things around that. What's happening in there is your control is still through the LTE system. Your call establishment, your billing, and everything happens through LTE. You're only offloaded to 5G NR to have data connectivity aspects. So the 5G network, 5G RAN still talks to the EPC, and the call establishment will have to be routed through the LTE network. Or in option 7, you have the other flexibility where you have introduced the 5G core, you have your limited 5G NR deployments, but then if you are already deployed nationwide or region-wise enhanced LTE, ELTE key difference, you can still have those ELTE networks talking to the 5G core in that particular option. Or you can actually have a mix of option 2 and option 4, where you have the 5G core in one end, but you are still relying on ELTE for your control and other things in the other end through dual connectivity modes. So this is what it is in summary. What is non-standalone and what is standalone? In the non-standalone, you are actually talking about dual connectivity. What exactly is that? The data is only transmitted over the 5G NR link, whereas data and control is actually transmitted over the 4G LTE network. Both the radios are simultaneously active and both are talking to your 4G EPC core. Why is it beautiful? It's beautiful because it's fast to launch. So if the operator already has the spectrum, if the operator is already willing to actually deploy NR services on day one, even before the core is deployed, this is readily available. And why do we people like it? Because voice over LTE is going to be the initial option for many of these operators. Or if you think that network function virtualization or SDN is going to be the key for you to start rolling 5G services, because that's where you see the opportunity, then you go for a standalone new core in that particular aspect. Okay, and this is another way of seeing this non-standalone standalone option. You have your non-standalone UE. It is actually connected to both the LTE RAN and the UE RAN simultaneously. So that is why it becomes a dual connectivity module. And then the user plane for the RAN is connected to the EPC. The control and user plane is actually connected in there. It gives you actually a list of flexibility in here because, say, for example, if an operator has got only 5 megahertz or 10 megahertz worth of LTE spectrum, but then somehow he got like 20 or 30, 40 megahertz worth of 5G spectrum which he could clear up, he can still start services where the control can be routed through your LTE system, and then your data is routed through the 5G RAN for NR services. As and when you start introducing your 5G only service, so you have your standalone UE get into the system, you have also deployed your next generation core into the network, your call gets routed in there. Enhancement happening in 3GPP actually allows for one more flexibility in terms of how you plan your network and your deployments. That's in the form of edge cloud actually coming into the system. So if you're talking about virtualization of RAN and other things, the edge cloud is actually moving towards your network. And if you're talking about mobile edge computing, then it is actually moving towards the RAN, which is actually closer to the network itself, base station itself. Moving next into the other part of the session, which is session 3 again, we discuss about dynamic spectrum sharing and explain why and how an operator today can leverage their LTE investments and then simultaneously do LTE and NR deployments on the same band, right? So what do I mean by that? Take the case of India today, right? So if you're talking about the 2300 or 2500 megahertz band, you already have operators like Airtel and Jio who have between 30 and 40 megahertz of 4G LTE spectrum, depending on which circle you're talking about. Similarly, Vodafone Idea has got 20 megahertz spectrum or 13 regions in the 2500 megahertz band. You can basically simultext LTE and NR in the same band through what is called as dynamic spectrum sharing, which is available since release 15. So the LTE control sharing is what you will do for enabling your 5G call. A better way to understand that is in here, right? So you are having your initial deployments. The 5G network will be evolving over the next case. All the networks, the 5G network deployments have used not standalone architecture, meaning that those deployments of 5G use the 4G core network and the 4G radio access, as I mentioned, signaling purposes. Okay, sorry. So when it comes to the deployment option, what you're seeing in here is there is this non-standalone UE, which is actually leveraging the low band LTE for its services. Through dual connectivity, it is actually connected to the LTE radio and the 5G NR radio at the same time. You can plan to actually have 5G in a higher band in this particular mode. How do you actually do it? Dynamic spectrum sharing, which is available since release 15 specification, allows the operator to use virtually any 4G spectrum now to be shared with 5G. So within the same spectrum, they can be simultaneously operate 4G and 5G and dynamically adjust to traffic demand and quickly move 5G to a lower band. So this will accelerate the way operators can expand the 5G coverage in their 4G band, which is needed to provide the continuity required to implement standalone networks. Right? So it actually serves two purposes. You are doing an early introduction of 5G in your system, and then it also actually move away from a 4G network into a fully fledged 5G network. Right? So take the example of our own operators, 2300 megahertz band. You are continuing to do 4G LTE service today. What if I want to anticipate that I will start doing some amount of 5G service in the same band, and as I migrate from EPC to the 5G core, I should be able to fully leverage that service. That is what is possible with DSS, and that is something which our operators are also considering to basically offer in the near future. So based on how you actually configure the network, you can actually offer the best of both the worlds, and you can actually offer better coverage service in this particular band. Okay. So let's see if we have questions in this particular region, because this is like a logical migration for me to get into the next part, which is 5G goes industry 4.0. So Sendil, if you are online, let's see if there are questions that need to be answered.
No, I don't see any questions. No.
Okay.
Okay. No.
So just one quick thing. So I have seen a couple of answers coming from the participants to my first question. So I think narrow frequency is the best option, that it comes under short wavelength, so we can be able to communicate. Okay. The second answer is 3, doesn't matter, with support of both dynamic and configured PUCH grant. Okay, great. So here is my way of seeing that particular part, right? So what is the challenge with millimeter wave band? The challenge with millimeter wave band is it's actually very wide. And since it is very wide, you have to actually pump in power over the entire band. Now, if you're actually pumping in power over the entire band over continuous time instances, then you're quickly draining off your battery. So the best way to actually deal with that is you actually transmit it in smaller epochs. So which means you are narrow in the frequency, narrow in time, but you try to use the maximum spectrum band that is available. So if you have like 1 gigahertz or 2 gigahertz worth of bandwidth available for you, target for very narrow epochs. So you just spark it, transmit over the entire band. That is the best way to actually save your battery. Right, so that's why the question was a little tricky, because I mentioned about the handset. So if you're talking about the uplink, epochs is better. If you're talking about downlink, probably it doesn't matter at all. Okay, I see that Sendil has also posted a question, so maybe you guys should also try to take a stab into that in the next few minutes. Sendil, can you confirm that the 2 questions I see are not new?
No, I don't see. The last question I see is about the 47 gigahertz. I don't see any other questions.
So please take over, Sendil. I will stop my share.
Okay. Thanks. I think you stopped at a very logical session where you spoke about migration and then using of LTE and 5G bands. I think I have a very connecting session. Okay. Let me know if you can see the slide now.
I can see it, Sendil. Go ahead.
Good. Thanks. So I think what I'm going to continue is about not just deployment, but a stage where you actually want to see what exactly is that you can offer coverage for a given parameter that you are looking at, right? So what we see is that the 3GPP specification, especially for NR, including FR1, FR2, there are a lot of parameters that you can actually change or tune or customize that what you want to deploy. It's not exactly hard-coded stuff, right? So you have subcarrier spacing variability, you have the amount of bandwidth that you can deploy. Right? There are a lot of variations that is available and customized and deployed. So we'll see that how do we look into from the capacity or a design cell capacity design perspective. Okay. So one of the key part that when we start saying, okay, I want to design an NR cell, the first thing that comes is saying, okay, what is the amount of traffic that we want to deliver from that site, right? So either it's 50 Mbps is what is the traffic that the site will deliver. Now the 50 Mbps could be delivered among one user, two user, or maybe even 20 users. So accordingly, the throughput that a particular user gets is definitely going to reduce based on the number of users. But then we need to look at saying what is the capacity of the site that is going to deliver it. That is one. Second is also is the quality of the coverage that you're going to deploy. So you may have a site where it says that okay, I'll be able to deliver 2 Mbps. But then we also need to say that is the 2 Mbps guaranteed to deliver for 95% of the coverage that you're planning for. So that's the second part, which is the quality of the coverage that you're planning. So it could be a simple input to the system that we are looking at is a 1 Mbps is what we are targeting for 95% of the coverage probability. So typically when we say 95% coverage probability is more like saying the cell edge, right? So when a user is at the cell edge, we are seeing that 95% of the users are covered. At that point, I still would want to deliver 1 Mbps. Now we'll come to the point where we say, is it an uplink throughput that we are looking at, or is it downlink throughput? And then for each of the cases, there are different ways to tune the parameters. the and then this is the top level input that we have fed into the system. Second part that we are looking at is that what band are we designing? Are we designing in a 3.5 gigahertz kind of a mid band, which is very prime band? Uh, is the band where most of the 5G deployments today in mid band is happening. And then we are looking at saying how much of bandwidth is available, what is the numerology. If it is a mid band, it could actually deploy with 15 kilohertz of carrier spacing or 30, or it could be 60 kilohertz of carrier spacing. So what numerology do you want to deploy there? Then it also depends on the different attributes to the system. What is the TDD configuration that we're looking at? Is it more TDD focused, more downlink focused, or uplink focused? Is it going to be symmetric? Right? That is another attribute that we're looking at. Then the other part that we are important to look at is it's not sitting in an Excel sheet and making a design and then say, okay, now we are going and deploying it. We also need to say what kind of site location it is. Is it a rural kind of environment? Is it an urban? Or it is a place where I see a lot of streets are there and a lot of buildings with a lot of glasses. It could be like a small street where on both the sides there are a lot of buildings with a lot of glasses reflections happening. Right? So a kind of reflecting that place where the deployment is happening is also important characters that we need to feed into the system. Right? Now, each site, we cannot have exactly the propagation, what is the path loss that we get in that each site, right? So typically what we do is we try to model them. And most of this model are categorized or bucketed into environments, rural, urban, and all those things. And similarly, we need to understand whether the transmitter and receiver, they are in a line of sight or not. Are they going to have non-line of sight? We still need to provide connectivity. So we need to plan for the worst case scenario. We need to see in an non-line of sight environment, can I still guarantee 1 Mbps? Or are you trying to plan to give service even to indoor? Then we need to see that, okay, if typically most of the sites or people are going to be indoor, then I need to see that at least 80% of the indoor houses are covered, or it is 90% of the indoor houses are covered. So we need to bring in those margins when you're designing the capacity and the coverage of the cell. Right? But to start with, we need to have something. Right? So we could say that let's say we want to start with a 1 kilometer coverage or maybe a 500-meter coverage. So that's the starting point of initial design of the system. Right? And then based on that, we look into saying, we try to find out what is a uplink cell capacity, what is the uplink cell edge throughput that you can do. Once you see that, okay, I am able to see a good cell edge on the uplink, now I go and say that with that parameters, what is the downlink throughput and the downlink coverage that I am getting. We need to see what is the downlink cell edge capacity or cell edge throughput. Are we able to deliver the capacity on the downlink also? If yes, we go down, and then the most critical part is looking into control channel. We'll come back and see that why control channels are important, right? And if control channel coverage cannot be met, if you started with say 400 meters, and with 400 meters you get a good UL and DL numbers, but then your control channel says, sorry, I can't go beyond 200 meters, then you need to stop. So with 200 meters of control channel, it doesn't matter whether you can give data or not. You need to have a bar before you start sending data. Right? So control channel is very important. So let's see, typically when we say a site capacity. Site capacity says how much of data traffic a site is pumping into the radio. So from a radio perspective, if I'm standing on a radio and looking from the antenna, it doesn't matter where I'm giving 1 Mbps for this user or 2 user, but I need to say, can I pump 100 Mbps of traffic from the site with 100 megahertz of bandwidth that is available to me. So that's a holistic picture that we're looking at. What is the site capacity that we're looking at? Now, it also needs to see that when I'm putting a site, what is it that on an average people will be consuming from that site? Is it not just at instantaneous, but I need to see for the 24 hours time window, right? So I think Ericsson mobility report is something which we publish very periodically, and a very reliable report which most of uh, people, even policymakers, refer to it. For example, they want to see what is the projection of average throughput or average data. For example, in the latest November 2020 report, it says because of this COVID, suddenly there has been average consumption of data per subscriber in a month has gone up. It has already hit 15 Gbps or something. So if I'm going to put a deploy network today, I need to plan that in another 5 years or 6 years down the lane, how much of more traffic a user is going to consume. It's always going to increase. So according to the report, it says about 37 GB of data is what a user will be consuming in a month, in assuming some active hours of 8 hours or something. Right. So if you look at that and then start looking, do a reverse calculation. So let's say, for example, if a site capacity is 50 Mbps, right? And then we see distributed saying between the downlink and uplink, 5 Mbps on uplink and downlink 50 Mbps. And then we look and saying, okay, there are 1,000 subscribers within that particular site who need to be served with a site capacity of 50 Mbps. When we say 50 Mbps, throughout the 24 hours, 50 Mbps of data throughput is being continuously pushed, right? And then it turns out that, okay, on a individual subscriber basis, if it's 55 kbps, assuming 10 hours continuously 55 kbps is being pushed, it turns out to be 6.9 GB per month. But then what we need to do is to go and do the reverse calculation. Go from 36 GB from here and then go back saying on an average I am interested in delivering 40 Mbps speed for a user. The maximum number of users that you can deliver is only this in a particular site. It also says how much of bandwidth is needed. Okay. And most critical part is always need to keep a check on what is the sellage throughput that a site will be delivering. Not the users who are sitting here, but if there is one site and then the other site is very far away, basically the site to site distance. If the site to site distance that you come up is say 4 kilometers, and then we see that at the edge sellage of both the cells, there are users who cannot go beyond or beyond 1 Mbps. It's going to be very bad. So sellage throughput that can be met with that kind of a design is very important, uplink as well as the downlink side. Yeah. So when we say uplink and downlink coverage, the way we define is the ability to transmit data channel. How far are we able to transmit the data channel with the given data rate? That is what we say is the coverage in uplink as well as in downlink. Now, all those data channels, whether it is PUSCH or it is PDSCH, they have a lot of other channels. In addition to the raw data that goes in, there are other channels which is very important. For example, before you start doing PDSH, you also need to have initial access, the broadcast information, or a PRAG signal that goes in, which says the network, the device boots up, it tries to connect to the network, finds the information, and then it says I need to send data, right? Then there is a downlink grant that is given on a common control channel, which says here are the resources on which you are allowed or scheduled to receive data. Then there is feedback that goes on HARC ACNACs are being transmitted on the PUCCH channel. So if you can notice, even if we are talking about the data coverage on PDSCH, you also need to see whether the corresponding PUCCH is also covered. Unless PUCCH is covered, even if you are able to reliably receive your data on the downlink, you're not able to tell the base station, hey, I got your data, right? The base station thinks you are in some coverage hole, you're not able to get the data, so it keeps on sending you or tries to reduce the data rate, right? So this is very important that these two are covered. That's the reason we will actually start from the uplink side. Then you have PUSCH, again the same thing, initial coverage is important. Then scheduling request is also goes on PUCCH, which says I want X amount of data that I need to transmit. Then you have a grant, scheduling grant is available on PDCCH, right? And then initial access includes this other channels, right? So now when we start doing, either we say that, okay, I'm going to design or put so many sites so that my control channels are covered well. And then you'll see that your data channels may actually have a larger coverage area. You are actually over designing your system, right? Because beyond certain so you need to have a balance between your control channel coverage design as well as your data channel. So one, if this, like I mentioned, if your control channel is not designed well, or your coverage for the control channel is not designed, you will never see, you'll never be able to access traffic at all. Or if your control channel, like broadcast channels, are planned to have a larger coverage area. For example, I was talking about having a beam-formed SSB is being transmitted, but your data is on a wide band. You may see a good signal bar on your phone, but whenever you start initiating a data, you'll never be able to send data. That is where you see that you're not able to establish data session. You only can see bars on your phone, right? So you need to have a good balance between control and the data. And I think by now most of us those are attending, we all know that downlink is at a power that base station is having a higher power compared to the uplink. The devices where you have a power limitations. Typical transmit power the UE has is about 23 dBm, right? And UE needs to adapt and do power control. It needs to say whether I'm close to the base station, away from the base station, and it needs to adjust its transmit power. Right? Six is that, hey guys, wherever you are in the network, I need to receive at least X dBm of power at my receiver. That is what the base station expects. Now, how does the UE know what is the power? The UE looks into the received signal strength and tries to do a calculation saying, okay, this is an open loop. It starts with an open loop part and sees that I need to at least increase my power so that this base station will be able to receive my signal at so and so target power the base station has set. This is a cell-wide information the base station sets. Right? So UE needs to increase its power. So let's look at so there is a power loop that happens between the UE and the base station. The UE needs to keep increasing the power, or there could be a point where you can say that, okay, my power is so low I cannot transmit, but can you reduce my resources that being transmitted in a very smaller chunk so that I'll be able to put all my power into one RBs, because that is very important. If you have a large chunk of RBs that you are scheduled, your power is distributed across RBs. And then if you try to decode the data within one RB, I think you'll not be able to decode it. I think this is a very good diagram which just illustrates this hysteresis, or maybe the stages at which this loop is happening. If you look at that initial stage, right, on the left hand side, what you see is an SINR. That SINR is based on the received signal per RB that base station is seeing. Okay, and on the x-axis, what you see is the path loss component. Basically, if you keep moving away from the base station, you see that you are moving on the right hand side and you have a larger path loss. When you have larger path loss, you need to increase your power. Right? So let's look at the initial case where the you are at a very close to the cell, and you see that the received power at the base station side is this, right, on the second y-axis, which is around minus this side, around minus 90, minus 96 or minus 95 something, right? And then basically what it sees is the base station has received the signal in a good strength, and it is able to see a good SNR in that region. So when the SNR is good, and then you keep moving away from the base station, what you see is this is the power, UE transmit power per RB, right? It needs to pump more and more power into the transmission. When I say when it is pumping more power, basically the base station, when you design, you're looking at showing the entire RBs are given for the UE to transmit. That's the first assumption. Entire RB is available for UE to do a play. With that, it needs to pump more and more power so that the power received over the smaller RBs keep increasing, right? So it keeps increasing that power, and then it comes to a point now it has saturated. I cannot put the entire power in the entire RBs now, right? So this is where you start seeing SNR goes down. So when SNR goes down, you'll not be able to deliver the same throughput. When SNR goes down, now this is where it says now I need to. So the power per RB is fixed now. You cannot do anything. Oops. So your received signal power at the base station has gone down. So your SNR goes down. This is where your throughput goes down. You now start doing adaptation. Your modulation index, your code rate, everything starts playing now. And then you hit to a point where at a certain level you cannot operate below that SNR value, or you cannot get that is the time where you cannot. The base station says now I need this much power. You're gone much below that. Okay. Once you come to that stage, right? The base station now says, now you are going below a certain SNR. What I need is that I need to reduce the number of RBs that is being scheduled for the UEs. Instead of putting the entire power in the entire band, now we reduce the band. Now I will say I am going to schedule with smaller chunks or less number of RBs to you. So now you see that the power is again added up to these RBs. Now you will start seeing the power per RB increases now, right? You're going away from the devices, and then you're increasing the power per RB by maintaining a constant SNR. So you keep decreasing the number of RBs available, and to extent where you see that now you have only one RB left. Your transmission cannot go beyond less than one RB. This is where you're stuck now. Only one RB is where you're putting all the power, and then your SNR goes below that level. So this is a kind of tuning that happens between the network and the device. This is something which the base station can decide when I should start scheduling it, what is a good time, should I keep the UE in loop or not. Right? This is completely up to the way you design this. Okay. So there are multiple dimensions to this problem, this particular loop. One, I cannot ask a UE which is at the cell edge to keep pumping more power, because pumping more power is not just helping me, but is also trying to interfere the users to the base station on the other side. Basically, you are increasing the interference level at the base station on the adjacent cells, right? And we also need to maintain that in the context of helping a user who is at the cell edge by allowing him to transmit more power, but he still gets lesser throughput, actually using the system very inefficiently. For one RB, I could have actually scheduled a very high throughput user inside the cell. So I would prefer not to do or not to underutilize or inefficiently use the system. I would better improve the cell design. That is an important aspect when we do the cell planning. Not to waste is realized in the initial days when network rollout is done. You would have less coverage, and you'll see that when I keep my phone in one of the room, my battery gets discharged. Why? Because you are seeing that the control channel keeps failing, the UE keeps trying to connect to the network. You'll see a lot of battery getting discharged. Right? Okay. And in all this design, what we discussed is just about just power control. We have not seen what exactly is the control channel coverage. So that is still an essential part. Okay, so how do we come back to this x-axis? What is the actual coupling loss that is brought in? So given with millimeter wave that is brought into the network, there are a lot of components that actually add and counterbalance this loss that is happening into the air link, right? So the coupling loss can be defined is brought up, sorry. The coupling loss includes now the propagation loss, which I mentioned about environment frequency and whether you're an LOS, non-LOS. Then the car penetration loss, whether if you're outdoor, are you inside a car, right? So typically you can see about 9 dB of car penetration loss can happen. And maybe that's a good reason why you should not talk while you're driving the car, right? You already, why do you want to operate at 9 dB below efficiency? And then you have oxygen absorption loss, which is maybe we can ignore for time being because it happens mostly in the 60 gigahertz carrier band. And then you have rain absorption loss. This is very important from the perspective of millimeter wave bands. I think you would have heard certainly a lot of people saying 28 gigahertz, when it rains, I don't think I lose it, right? So you need to ensure that when you're budgeting the cell planning, you have that margin in the design. Now, it also depends on the terrain. I don't have to put a big margin where in places where never a snowfall is going to happen. I don't have to put a margin where there is no rain that is going to happen. So these are things which is very necessary to know where you're going to deploy the network, right? And then you have body loss, which I mentioned earlier, and then material loss. So this material loss, basically 3GPP, if you look at the T8901, has this model which says if the buildings are lot of glasses and less concrete, or it is more glasses, less concrete, how do you balance? What is the proportion of that? Accordingly, you need to include those losses in your calculation. And then foliage loss. Foliage loss is mainly due to the vegetation that you have. And this also plays a very important role, especially in the millimeter wave band. The reason is most of the mid-band radios, they are at a very high height, right, compared to the high-band radios, which could be even below rooftop or even a street pole. So when you're at a street level height, you actually see trees are also on the same height. So you'll see that the millimeter wave signals are actually passing through the foliages. So for every 1 meter, there is a foliage loss that can happen, right? So you also need to see how your height is and how much of vegetation is there around those sites. That's another important part. We'll see in the next slide. Okay. So I think I covered both. Yeah, yeah. So this is how the foliage loss is seen, right? So you have a base station, and then whether you are inside this so many trees behind it, and then your base station is sufficiently at an elevated height, you would see that the foliage loss will be much less because you have a direct, only this much portion is actually passing through the foliage. Whereas if the patient is at a street level and you have good gardens around you, luckily, you will see that you are actually seeing poor, there is a lot of loss because of the foliages. Okay. So you can see that for a 2 meter distance of trees well inside with 28 gigahertz band, you can actually hit all the way till 12 dB of loss. This is important to design in your design. Okay. So given that you have looked into I think one of the important part which I missed here. So compared to LTE, when you're looking at NR, we discussed earlier about this active antenna systems and the beams. There is a way how each site could have, for example, the data channel could be on a wide beam or it could be on a narrow beam. Based on that, you need to find out what exactly is the gain that you're giving for that particular channel. So you cannot just say this path loss is fixed. The path loss would vary based on what channels you're looking at, whether it is a data channel, uplink channel, or is it a control channel on the downlink, right? So accordingly, you need to insert the corresponding gain from the beamforming. That comes out and says that, okay, that's one reason. This is what we call as a link budget. So if you look at the submission from 3GPP report 37910, which includes an Excel sheet where you can play around, which basically gives for a downlink and the uplink for a data channel as well as the control channel for all cases, LOS, non-LOS, or outdoor to indoor, right? So what are the typical losses that can happen? And then for a given loss, if I need to ensure that, I think the initial part of the sheet, this basically has more than 30-40 rows. It can say that if I want to have a 90% reliable coverage with X throughput, what is it that I can lead? So if you look at this highlighted portion, which says that NRPUCCH, I believe it is PSCH. Okay. So the least range that you see here is the PUCCH as 870 meters is the coverage. And this sheet I think is a 4 gigahertz for a dense urban case, right? Now you have a good downlink coverage around 1.5 kilometer, but then the most least one is around 316 meters. which is the data channel coverage is limited for uplink. So now this gives a good idea saying, okay, you cannot design a cell or put two sites with an ISD of 1.5 kilometer. Your cell ISD has to be based on this number, which is the limiting one. Okay. So given that, uh, so this gives a bad impression, saying, okay, we have a lot of issues in the millimeter wave band, the propagation loss are going to hit us. But then what we discussed till now is only about purely looking at one NR carrier, right? And we have been seeing that, like in the previous session, what Vinosh talked about is about the deployment is not going to be one just NR carrier. Either it is going to have additional carriers from LTE, additional bands, right? You have more radio channels through which you're going to communicate. So what we see here is how do we improve the uplink capacity? We know that the uplink is limited, right? So if you look at this initial plot, this is from Ericsson's technical review paper, technology review paper. So if you look at this area, where most of this downlink is very good. You see the green part is about 400 Mbps most of the cases, right, in most areas, except for some small areas where you have it just hits 100, 200 Mbps. Now, if you look at the corresponding uplink, you see there are a lot of coverage holes. I'm not sure if you can see a circle here. Maybe I should point out. Yeah. So here you can see a circle which basically points out there are a lot of uplink coverage holes. Now these are places there is no uplink happening. So whatever green you see does not matter. So I remember during my PhD time when we used to do simulations, I found that simulating downlink was much easier to run algorithms and check it. Right. So most of the time I used to get interesting saying, oh, I got a curve shifted towards right. I think I got 3 or 2 dB gain. But the perspective of looking from an entire system is important, right? You may see a very good downlink throughput, but that does not realize that the system will work because your uplink still has a lot of coverage holes. So it has to be seen in this context: uplink, downlink, control, everything together. Now, if you try to combine this system with an LTE network, now the system where we are comparing here is an LTE network with 50 megahertz, where you use the same grid of 800 megahertz, 1.8 and 2.6 because you don't have large bandwidths available in single band, right? So basically, we are combining all the three LTE bands. Now, if you look at, you'll see that these coverage holes are gone. There are no out of coverage users, right? So what has happened here is it's not that we have overcome the propagation losses. What the network does is something smart. What it does, those users whom the NR could not address, for example, here, I would want LTE to spend most of its RBs to those users. Instead, and all those users were in the good coverage in 3.5, I'm going to say the LTE band, saying the LTE radio, saying that the NR will actually serve those users, whereas the LTE will start serving those users who are in the beyond the 3.5 uplink coverage region. So this way, both the technology, when radios are used together, you will be able to address these coverage holes. This is the way how you can actually build networks, and this is what practically is done. So when the network planning is done, it is not done in an isolated way. So it is always seen with a good umbrella control channel which can actually cover NR also. Now let's look at another example. Let's say we have a 2G network which is typically having operating at 800 megahertz band, and we know that we used to have very high tall towers of 2G network and compared to LTE network, right? And then they used to have a larger coverage also. In those LT 2G grade, if you start deploying an LTE network, you see that look at the coupling loss that we see here. So if you look at the LTE 800 band at a 5 percentile case, you have minus 140 dB of coupling loss, and this is based on a 4 kilometer ISD. Now, if you look only a pure NR sectorized antenna, it is actually much worse, right? It has actually shifted towards the left. But then if you can leverage AAS antenna on those 3.5 gigahertz, you have a narrow beam, you actually have a larger coverage that you can bring in. So you'll be able to handle larger coupling losses. So now that is come close to the LTE, right? So this we are talking about the control channel. What if we start doing both the radios together? We can use the same logic where you say that wherever 3.5 gigahertz coverage ends, we want LTE to take over and then LTE starts serving those users. And you cannot increase the UE power. We are still assuming that UE power is limited. We are not going for a new form factors, right? So what we do is, if you look at this downlink throughput, we are trying to push more and more traffic from the cell. If you see, what does it mean by pushing more traffic for a macro cell? Initially, the demand was 50 Mbps, or say, let's just look at this part where it says 10 Mbps is what a traffic that the network is, the site is trying to push in. And if there are more cell edge users, it will not be able to deliver that traffic evenly to the cell edge users. More demand is coming from the in-cell guys, right? So then we see that at the cell edge or the 5 percentile throughput for an LTE, it actually falls down with the more traffic being pumped in, because more traffic is being pushed to the cell in-cell users, and then the cell edge throughput goes down. With the NR 3.5 gigahertz, this one you'll see the and this one is for the DL, where you see that the cell edge throughput actually ends around 250 to 60 of for the cell average traffic from the cell side. Whereas if you combine both LTE and NR, you could see that you can actually pump more throughput, which hits all the way till 300 Mbps also, right? And the corresponding cell edge throughput is still around 20 Mbps at a 250 number. What is interesting is in the uplink side. If you look at the NR 3.5 at a 5 percentile, it's almost negligible, right? So we have a negligible uplink user throughput for 5 percentile users. And if you try to see an LTE, which again ends exactly around 5 Mbps for the traffic capacity. When you combine both, what is happening is now NR is able to add capacity to those all LTE users who are close to the cell, and then the LTE spectrum is now free to start serving all those users who are at the cell edge. You can see that this is a very healthy cell that you are able to deliver instead of almost no coverage gap or a shorter, smaller coverage from the LTE network. So this is part of the deployment case. It's not something what a specification says how to do it. So this is something that looks into the environment, how you design it, and leverage the existing specification to for the deployment. And the last slide I would want to end up here is when we see the other two slides are talking about the midband case, where we are trying to see how to improve the coverage as well as capacity of the network by combining LTE and NR in midband. And recently in August, what we did is along with Ericsson, Qualcomm, and CASA system is a CPE builder. They build a CPE based on a commercial modem, a millimeter wave modem. It actually, we were able to deliver over the air about 3.8 kilometers, and that's a kind of throughput that was achieved with millimeter wave band. So typically we have been assuming that okay, millimeter wave band has a lot of path loss, and we may not go beyond 200 meters. So we were able to do that, and that was demonstrated. And then recently this month we actually did it over a live network on Teams network at 6.5 kilometer in a 26 gigahertz band. A speed of 1 Gbps was delivered, and that was tested with both UDP as well as the TCP sessions. Now, this is a question which I want you to think about. When we started in the millimeter wave spectrum for NR design, we saw challenges, right? We said the symbol duration is less, the CP durations are lower because you're looking at higher subcarrier spacing, so that it cannot handle larger delay spread. But then when you increase the cell coverage, the propagation time, that there needs to be time that the device, sorry, the data when it reaches to the base station needs to be time aligned with the downlink, right? How do you do timing advance? How do you ensure that the path loss that happens is within still the CP? So this is, you need to think around how to do that. I think with this thought, I will end the session here now and leave it to Vinosh.
Thank you, Sendil. I think it was like a very good session. Um we have some chats and then we have some questions that is coming up. So quickly looking into the chats first, there was a question you had posted earlier. What is, in your opinion, the right approach for transmitting SSB, wideband, wide beam, narrow beam, and why? There is one response which says first wide beam for initial search sweep, then narrow beam once search is completed. I think that's the right answer. You have any different take?
Yes, I would say both yes and no. I think this it depends on implementation. I think different network vendors differently deploy, right? It also depends saying, okay, if I want to do a drive test and see, oh, which network has good bars, right? So in that case, you would see that, okay, if I have good narrow beams, if I keep searching, I'll see very good, nice SSB blocks are decoded. I can see the network is good. But then that is one way of looking at it. It is up to where you're deploying it, right? So if there are a lot of mobility and then users coming in and off, you need to see that as soon as I come to a small spot where the NR site is there, I need to immediately start and initially connect to it. It depends on that because you should also be able to do it. And the wide beams, actually, if you're looking for a site where we know that most of the time the initial access is happening only for a less frequently, then you don't have to pump more power in each directional beams. Right? So you could start with saying only a wide beam and leave it because you don't want to spend power in those beams and use the beams for pushing more traffic channel. So the answer is both. I would not say the answer is wrong because it will depend on where you're going to deploy it. So it's up to implementation and site specific solution that you want to look at. That's how it will be.
Thank you. And then there was a third question posted by me, which says, which network defines the performance of a dual connectivity system and why? The options which were later modified as LTE, NR, and both. And I see the response that LTE as the master node drives the performance, right? Which is again the right answer. The reason being, in a dual connectivity system, the control is always routed through the LTE network, right? So, and the control defines the performance of a network. If the control fails, the call will have to drop. So even if you have very good coverage in NR, as long as the LTE channel is not able to meet and exceed it, it doesn't matter at all. And the same thing was also experienced in the LTE only networks also, that if your coverage doesn't, if your control doesn't reach a particular point in your cell deployment, your call will not be established. So you have to basically do a lot of other cell deployments. Okay. And there was one more question which was posted.
Yeah, before you jump in next question, I think this is exactly the point that which connects to the previous design problem, right? So now you start seeing why these options were important. If you look at if the control channel informations are actually coming from LTE, then when you're doing an NR design, you don't have to worry much about that. So now you know the reason why this split is helping. The control going from LTE and this NR you have for the data part.
There was one question which came in, can base stations able to know perfectly about the power and SNR profile as UEs may be mobile? And the answer to that is yes, because the G node B or the E node B in the LTE case, they continuously monitor the UE health and basically in the form of the uplink reference signals. In the 5G world, you have sounding reference signals also, which help to find out how placed these UEs are. So every uplink transmission happening, there is data and there is a reference signal that comes along with it. So the G node B measures that, and based on that, it actually gives a downlink and uplink grad to it. Moving back to the question section, depending on the last things which are posted. Okay, so Sendil, you may want to take this. What are the advances in automated cell planning?
Yes, very interesting. So, if you look at radios today, I think most of the time you would have seen that we would say that Ericsson's radios, which are already there in the network, are 5G ready. What does it mean? Is that they are capable of doing radio processing what an NR can do today, right? So if you have enough computation power on the baseband, like what Vinosh just mentioned about this SNR profiling can happen, right? And he also mentioned about that 5G, the design philosophy was service based architecture. Means maybe it's more of a philosophy, but you will be able to connect with, we know that software as a service, infrastructure as a service, right? Google Cloud Platform allows different ways of taking it. So what the 5G specification, the standard, the way they're developing is each of these services that's happening, whether it is a function of authentication or it is a radio function that is happening, it can allow to expose the KPIs as APIs, right? It can reflect the metrics that's happening in the radio. So if you have enough computation power on the baseband, these metrics can be learned using AI or something. It can also help saying, okay, I need to tune the way this radio site has been planned. Now there are reasons why you want to do it. For example, look at a private factory or industry case. You have only few sites, say for example 4 or 5 radios need to be put in. You can't go into a big machine which is there and find out a location where you can go and mount that radio. You would want that edge core sitting into the same factory premises should be able to query those radios and tell me how many other radios are you scanning, are able to see, look into feedback, and then it can reconfigure the radios to see what is the coverage it wants to do, it, what power it wants to set, all those things. So this kind of planning is possible to do even on the floor itself when it is deployed. So that is something which we use AI also, and I think maybe you should look into Ericsson's portfolio for Indoors side, which actually does this kind of stuff on for deployment.
Yeah. I think the next question is again comes to you. It's a little tricky one. I will basically rephrase it for you based on how I understood it. So during network dimensioning and trying to find out how the infra will have to be planned, how will you provision for network switches and routers based on the capacity and coverage slide which you just presented?
So this planning is only talking about the radio capability coverage, right? So once you know that, so looking at a region or area that you're looking at, if you look at the simulation that I showed, the simulation is not about just one site, right? So it's about how many square kilometer areas are you planning the network for. It says within this X square kilometer of area, what is the population, what is the population that will actually go in another 4 or 5 years. Based on that, how much of cell capacity is needed for each site to deliver it. Then you look at saying, okay, how many sites I actually plan to deploy a fiber, or if not, at least which are the good, I would say, a favorable locations where a fiber can be deployed at that point. And then from there, you need to have the microwaves to connect to give a backhaul to them. So it's a long process. So whatever we saw today is in isolation of just one site, but it actually ends into saying what is the transport requirement also. I hope I helped in clarifying, or did I confuse more?
No, I think that's the right answer. So this network planning is only about the radio part. The question was about how the network related planning need to be done. They have to be concurrently done. It again depends on what particular switch, what particular router. I think the quick and escape answer to that will be, if you are doing for a current planning, then maybe the capacity coverage gives you some idea. But typically networks are not planned for that way. They are actually planned to accommodate more capacity in months and years to come. And they typically don't change this within like 2 to 3 year time frame. And these are generally upgradable. So it doesn't matter really. That's sort of my response to it.
Yeah, I think maybe one something that we need to add here. This is exactly the reason when the networks are deployed, you see to that it runs to a capacity of 50, 60, and then the moment it hits certain capacity, this is the time when an operator feels what will happen. Suddenly there is a surge. I need to plan. I need to get more spectrum. So this is the reason why leading countries actually have a roadmap saying in every 4 years or 3 years, I need to ensure that more and more spectrum are released so that operators can plan So they need to, it cannot be like an one-time investment. You did it and you stop. So they need to plan this, saying, okay, over so and so years, I need to have this ready. And that's also a reason why this demand goes all the way to WRC and other thing to get the spectrum released. I think things are connected. So one important part, in addition to the spectrum, I think very relevant for what you are going to present is about the way these network slices are designed. This is exactly where you need to see that how much of delay between these hops gets introduced, whether you'll be able to deliver certain network slices and services or not for industrial use cases. I think there it really plays an important role. Okay, over to you. I think.
Thank you. Can you unshare so that I can share?
Yeah.
Can you confirm that you can see? Yeah, thank you. Yeah, so now we get into the last part of this session where I basically discuss about 5G going industry 4.0, why basically we want to do this and what exactly is the option, right? So, of course, nobody does anything if there is no commercial aspect associated with it, right? So, I think a few years back, we basically looked into a study which said, the 5G economy and how 5G technology will contribute to the global economy through IHS economics and IHS technology. So what we figured out was by 2035, about $5 trillion worth of uh, uh, economic output can be actually triggered if 5G is rolled out in time. And the key thing we actually figured out in there was manufacturing sector will contribute to about 70% or more of what this is about to offer, right? And that is where you are actually seeing too much interest in the manufacturing sector. Germany calls it Industry 4.0, US calls it something else. Japan, which is like an industrialized nation, is actually all going to go on ensuring that its factories are automated for the future and other related things. So let's see, what exactly is this Industry 4.0 and why exactly is there so much excitation to it. So here is one example of how a factory of the future is going to look like, right? So this guy is actually taking a tab which actually monitors a lot of these things. There are tons of stuff on the ground from everything related to industrial robots, wireless edge analytics, sensors, computer vision, head-mounted display, handheld terminals, AGVs. You see tons of them in the floor. And if you can actually classify them, they get classified into one or more of these three verticals which were studied for 5G. You have your ENBB, you have your URLLC, and you have your massive IoT use cases. Each one of them have very different requirement for latency, availability, and the data rate they are expecting. A sensor may be just pumping in kilobits worth of data, but then it expects the availability to be very high and the latency to be very low. A handheld terminal, it can actually pump in information in Mbps range, or if it is a head-mounted display which is actually capturing video and then sharing it with you, it's actually pumping information in Gbps tone. So there are it's a catch situation, right? Because considering some of the use cases in the future, we see that the desire for everything to be connected and connected wirelessly, to be very precise. When these examples are examined, it's clear they sit on the three pillars. That's also very evident. So considering 5G as a whole, the new radio technology and the core network we think of in each of these pillars reside within a factory floor. So ensuring that these are served will need 5G to be in place. And how do we actually serve it? Is it through public network or is it private network? That's an option again left for the regulators and the service providers to figure it out. So 5G takes this Industry 4.0 to the next level. It's not only about the connectivity and security aspects, it's also about compute, edge computing and other things that comes in and then becomes part of it. So what is Industry 4.0? That's going to be your Industry 3.0, which digitization along with 5G connectivity. So the earlier a country deploys 5G connectivity, the sooner it will be able to get into the next big industrial revolution through automation and performance related aspects. So how do we do it? It will have to serve through designing 5G to meet industrial IoT requirements, and depending on what particular capability it actually brings in, you call it a private network. You define it through a licensed shared or unlicensed spectrum. bring it through Ethernet and time-sensitive networking and through positioning and accuracy in the thing. And that actually comes in through different things which became part of different aspects which became part of 3GPP specifications recently. And as I mentioned earlier in, I think, my fourth or fifth slide of this of session 1, the standardization of these information exchanges, APIs and other things happens in 3GPP. But a lot of these use case requirement study, ecosystem movements and other things happens in a platform called 5G ACIA, which is about the traditional infra industry and the connectivity industry coming together and then developing these solutions. So because it's targeting a particular group and a particular set of services, the network performance can be optimized such as in case of latency. Another benefit is that the data can be kept local. This can be an important consideration for critical industrial IoT operations. Of course, the security standard for cellular systems has been super high with great track record over the decades. So this automation industry is actually leveraging a lot of these, if I may call the word, investment made into 3GPP cellular system design, which is quickly leveraged into the network rollout. Private network is not for 5G only. One can have private LTE networks today. Example, the CBRS, which is used in the US. 5G of total, release 15, 16 tomorrow and other things come up. They actually define how this will be basically having advancement with. Seamless mobility can be supported between private network and public network. So if I were to migrate my network into a future network, which is through automation, how does that actually happen? So today your factory floor is defined through servers, controllers, your industrial Ethernet like Profinet and other things connected to machinery, remote IO, proxy, and other field devices. This is typical of any of these things existing today. The objective is to replace Ethernet switches and the wiring with 5G in a manner that is transparent to the end machines, because the machines you are not going to change. Right? The machines and the power line communication devices do not need to be aware whether the Ethernet frames are carried over 5G or through Ethernet. This can be done by introducing 5G Ethernet adoption, where the end machines can connect it to UEs via Ethernet, and the local 5G core network connect via Ethernet to the industrial Ethernet infrastructure. So from the perspective of other equipment, 5G systems will act as an Ethernet switch to the time-sensitive network that it has to support. To do this, there are certain features that the 5G systems need to enhance. So that's how the transformation is actually going to happen in today's factories and make it factories of the future. So how does 5G bring support for time-sensitive networking? So in order to deploy 5G for new and diverse use cases, including Industry 4.0 and factory automation, the 5G system must work in harmony with the communication technology used in such industries. For this purpose, 3GPP has made significant progress towards the integration of the 5G system with IEEE 802.1 working group, specifications covering time-sensitive networking. The vertical LAN work item in 3GPP release 16 introduced the support for time-sensitive communications by seamlessly integrating the 5G system as a bridge to IEEE TSN. The IEEE TSN set of specification is considered the convergence technology that will enable deterministic and low latency communication in the factories of the future. 5G TSN, or 5G time-sensitive communication, is a service that supports deterministic and asynchronous communication, the active communication system with high reliability and availability. It provides packet transport with QoS characteristics such as bounded latency and reliability, where end-to-end system and relay transient nodes can be strictly synchronized. 3GPP supports TSN by considering the entire end-to-end 5G system as an IEEE 802.1 AS time-aware system. Okay. Moving quickly, how does 5G comp achieve this thing? So Sendil mentioned about multiple transmit receive pairs, beamforming, and other related things. So what is tricky in this network is, without WAS, how do you continuously monitor and scan AGV or other things roaming into the network? So I have few videos which have been captured in one of the trials we had been doing with Siemens, and explain how this thing actually happens over real time. So these are proof of concepts which I'm allowed to now share. But with Siemens in their plant in Germany, we actually have real life trials going on, which they are actually leveraging in their network transformation to Industry 4.0. Using antennas and networks deployed in the 3.7 and 3.8 gigahertz band through 100 megahertz bandwidth, we were able to access and connect with different things, elements in the network, and also ensuring that the safety and other related protocols were maintained within the factory floor. So looking into a time-sensitive networking demo, this is something which I participated when we did the trial in San Diego last year. The idea is what happens if it's a self-depicting demo. It's actually good to see rather than me talking. So the camera monitors, the different TRPs receive it, the robot reacts to it in real time. And then it enables it. This one explains, what will happen if TSN is enabled and TSN is not enabled. So when TSN is switched on, the robot is precise in the functioning. It will be able to quickly sort it out. When it is not switched on, it misses a lot of these samples. That explains, why it is super critical for industry floor to be needing industry grade 5G network in the system. The high latency, high availability, high bandwidth, local control, local data, local exploitation. So the connectivity, compute, security, it all becomes part of what we will be offering in that particular industrial environment. So as you can see, every equipment is actually served by every transmit receive pair in the factory floor. So even if there are like people moving or AGVs moving or some other interference coming into the factory floor and blocking away some of your signals, the factory floor will still be able to function effectively. You'll see that, as the blocking happens, how the signal quality degrades. And when you enable URC, which is like multi-TRP transmission and reception, doesn't matter what happens with one signal getting blocked, your availability is going to be high. So the aim in here was basically to sell two things. One is explaining that 5G actually has all these capabilities. The second thing is, just because 5G is available doesn't mean a player like a Siemens or somebody is actually going to quickly adopt it. You have to do tons and tons of these testing with the operator, with the service provider, with the end user, in ensuring that they get the comfort, and that is what moves the ecosystem. That's what moves the digital economy. The last one is about precise position demo. This can be just your Amazon main centers or something which collects, stores, and retransmits packets in every big city nowadays. So that's the bird's eye view of how many different transmit receive pairs are actually coordinating with that AGV in actually placing, positioning, and doing that. And remember, the key thing is indoor positioning. It was not about XY coordinates alone, it was also having a Z coordinates, where vertically it was able to position the exact location where the packet had to be kept. So NR, when it was designed, it was also optimized for indoor positioning related enhancements. Okay, with that, in the interest of time, let me just move forward. Let me just go into explaining what is the future of 5G, where we are today, and what to expect in the days to come. Right. So, for the first time, I want to basically show this particular slide, basically summarizing what I had explained earlier and what Sendil had also explained earlier. That 5G is not only about your mobile phone and trying to give broadband coverage. It is actually about a lot of other aspects, other opportunities, other businesses which will start using it. Right. So you are seeing a tons of mobiles in here, mobile handsets. You're also seeing a lot of these modules, CPEs. You're talking about 5G enabled laptops, which will not just help you connected always, but also connect basically to your enterprise cloud and other related applications. So the target market for 5G coming in, it's about many different use cases. I think as of 2020 end, the GSA clocked it about 700 plus 500 5G designs which were launched or in the development or getting almost available. So a huge opportunity and a huge way of actually seeing where this will actually move, right? So just to get a feel for what exactly is happening in here, if you can see this particular slide, it's about a virtual telepresence collaboration where a factory floor is in one place and then a participant is actually joining in from a very different location. So the particular graphic designer from Sao Paulo is actually talking to an end customer who is based out of Istanbul, communicating through virtual XR platforms and experiencing through virtual reality on what exactly they are planning. Although this sounds like futuristic for now, we are personally aware of entities who are trialing this now in real time, right? And 1 year back, when COVID was still not away from India, we were not talking about online meetings happening the way it is today, right? So in the near future, we will also see tons of other applications coming in this way. With that being said, split rendering, AR, VR, XR, that's going to be the next killer application which will actually come in. So I bet a few of our participants are already aware of interest from a couple of our operators in actually having split rendering XR, VR into education platforms and tools they are currently developing. So where exactly are we in terms of the IoT skills, right? So release 15.16 when 3GPP developed, a lot of these use cases were about eMBB and URLLC. Then came NR Lite. So NR Lite is aimed at use cases that have low complexity and relaxed requirements as compared to high performance IoT, but still has high data and computational requirement, along with power dissipation as compared to massive IoT, which is now mainly addressed by narrowband technologies. However, we ensured that the 5G to be unified connectivity fabric. So we could see 5G future NR, which will actually be simplified and then integrate these particular aspects as well. In terms of timeline, driving the 5G technology evolution, here is where we are, right? So before pre-2018, 3GPP started doing this work on release 15 study. They also made release 16, which is like a complete package of 3GPP's 5G story. We are currently here in early 2021 when release 15 based 5G NR and early release 16 based things are already commercial. As we progress in time, going into release 16 and 17 and 18, you will start to see commercialization happening with a lag of like year, 2 and max 2.5 years time. So when we reach release 18 enhancements, there will be continuous expansion into new verticals, deployments, use cases, and spectrum. 3GPP today is doing release 17 specification, which is targeting low complexity, NR Lite, XR, high precision positioning, and things around that. So what exactly happened from release 15 going into release 16? We spoke about release 15 about flexible slot-based framework, numerology, coding, massive MIMO, and millimeter wave. As this progressed into release 16, we discussed a lot of advanced power-saving mobility, unlicensed spectrum, high precision positioning, mission-critical design, new deployment models, and then the sideline. There were tons of enhancements that came into expanding the reach of 5G, driving the foundational enhancements. And as we look into the future prospect into release 17, you'll be seeing new elements actually coming into the puzzle. There will be centimeter accuracy IIoT with millimeter wave, enhancements to 5G NR industrial design, enhanced downlink uplink MIMO, NR Lite, integrated access and backhaul IAB with more flexible and capable opportunities, getting into unlicensed spectrum, talking about spectrum above 52.6 gigahertz, which was not studied until now, expanding sidelink to V2X, continued EMBB, and a lot of other opportunities like drone and others that are actually coming in. So after 5G, there should be something. So what is that? Yes, you will be starting to see 6G happening, and then hopefully around 3 or 4 year timeline, when ITU starts developing the vision framework, that will be when the first kickoff action for 6G standardization that will happen globally. Traditionally, it has always been ITU which forms the vision, and then there are a lot of these ecosystem players and others who will contribute to developing what will be the framework, what will be the opportunity, how do we actually do it. So if you look into it, the 5G platform, it's going to be like it's an innovative platform. And the same innovation cycle will apply into the next decade, getting into 6G. What is fundamentally different is 5G's unified flexible framework, which will also incorporate a lot of other things going into 6G. Regardless it is called as 6G or something else, there will be always opportunities to innovate and contribute to that. And looking into like my last slide into what exactly this is going to be, in terms of timeline, objectives, and other related aspects, long-term R&D, research, and collaboration in that particular mode, that is going to be key to it. There will be a lot of new enhancements that will be coming in 3GPP between 5G and 6G in terms of enhancements, extra enhancement, other related things. That is going to span all the way up to release 18 and 19, hopefully in my view. And then in release 20, we should be starting to see this getting into 6G framework. And I'm hopeful that this will be sometime between WRC 27 and WRC 31. That will be the hotspot when you will actually see 6G impacting into your network. With that, we have come to the concluding end. And let's see if there are questions being posted. Sendil, do you observe something which we need to answer?
Yeah, I think there's one good relevant question that could be you can take up is from Jose Aragon. Is there a need for alternative networks to move data insensitive to latency, or it is expected that 5G and future generations will be ubiquitous and deal with the increasing amount of data?
You want to answer that? You want me to answer?
You can take up, because I think this is something what you just mentioned about 5G to 6G and all the stuff, right?
So two things, right? So when 5G came in, the priority was EMBB. So release 15 and to some extent release 16 focused a lot on EMBB applications. So that is where you're actually seeing even in 5G deployments, you have NR focusing on EMBB and URLC use cases, but we continue to rely on narrowband IoT for your IoT applications. That is now slowly migrating into NR-based NR Lite or whatever marketing term that will come for that. Similarly, even in release 17 timeframe, we are talking about LTE based ENTV, which is the broadcast solution for 5G. The same way, it will actually now coexist with some other technologies, say for example Wi-Fi for offloading some other things. But as time progresses, and in my view, like release 17, 18, and hopefully 19 timeframe, NR would have actually encompassed a lot of these other use cases which can happen. And as I mentioned, ubiquitous technology. So this will be now able to handle a lot of these use cases that will come in that place.
Okay, there is one more question, Vinosh. This is from Dr. Rajiv Shure. Question is, cannot Industry 4.0 indoor applications be enabled by Wi-Fi 6, Wi-Fi 7, and or Li-Fi?
Sendil, you want to take first?
Yeah, I think it'll be too generic to say Industry 4 applications. Like what he showed is a bunch of different services. I think what you need to say is when you say Industry 4, it's not just time critical. There are a lot of applications which are not time critical. So it's a mix of all kind of services that has to be packed together. So it may not be a straightforward answer to say whether just one technology, whether it is Wi-Fi 6 or unlicensed application is enough. I think it has to be bucketed so that all the data that is originating from the floor can actually get aggregated before any decisions can be made. So it has to be a combination of that radios that will happen.
Okay.
Maybe Vinosh can add more on Wi-Fi 6 capabilities.
I'm just trying to see if I can localize on that particular slide. Yeah. So if you look into the end of this particular slide, it actually talks about all the three use cases being addressed by the same technology, right? So massive IoT and URLC use cases are today addressed by NR standard. The enhanced mobile broadband use case, yes, I agree, .11 AC or .11 AYAX, they can actually satisfy that particular use case. So you still need something like NR to actually complement for the URLC and the massive MTC use case. So yes, there is a possibility, but it has to be then going to be like a mix of technologies, not one unified thing. So an operator will have to then deploy NR solution as well as Wi-Fi access point to actually offer that service.
Okay. And one more question from Rajiv is, are there any concrete results on the performance of network slicing?
Maybe I don't know how do you define performance because there are multiple KPIs that has been introduced for monitoring a slice. So I don't have any published results about it, but then it's multiple KPIs that will be monitored before I say that this is a KPI that is needed for a given slice.
Okay.
And if that slice cannot be delivered or target all those requirements of that, the slice has to be. I mean, you can't run that service on that slice.
Okay. And one last question from Rahul. With private 5G being adopted by enterprises in future, will the enterprises be expected to replace all their existing indoor access points to support 5G? I believe the question is, yeah, whether there's a need to replace all the Wi-Fi access points so that you can provide, enterprise services via 5G.
Maybe let me. I think that's a little bit of mix of thing how the way it sees, right. When we say enterprise services means whether the factory floor, for example, I am going to monitor people entering and going the factory, right. That can still on be a Wi-Fi. I don't have to depend on a third party or maybe an actual network being deployed to just take their video feed, right. So I'm not sure if an enterprise himself will actually say that I want to replace all the access points. He will still use the access points for things which need not to interact with the other machines which are operating. Or even if they're operating, they can still talk to it. For example, I remember talking to one of the uh, I don't know the name. So basically, they were looking at they want to digitize a particular floor. They said we have a switch on the top of at least two or three floor rate machine. The only thing is that we need to go up and see whether the red light is on. I want to turn on. They said, do I need to get into a private network for that? He said, how many seconds does it go and do it. So no, it's not that critical. We can always go walk and do it in another 4 or 5 seconds. In that case, even a Wi-Fi access point connected to it or even a Zigbee can solve the problem. So I don't think we should try to force fit everything with a single solution.
Okay. And one last question from my side. Vinosh, you briefly touched upon NRU. So for NRU, since there's a lot of talk now about 6 gigahertz band, can you shed some light on what performance we can expect in the 6 gigahertz band when it comes to coexistence between 5G and Wi-Fi?
You asked me the most tricky question. So let me try to be okay.
I'm
So
looking for a technical answer, not a political answer.
okay. So the key thing is Wi-Fi 6 is going to be the target for that particular band, right? And that specification is complete. 3GPP NRU is still work in progress, and they are trying to compete with Wi-Fi 6 and actually becoming a candidate for that particular band. So a latecomer, which knows which particular benchmark it needs to beat, will obviously beat it.
Okay.
But an early adopter of technology, if it has the right metrics, they will go and occupy that spectrum, and then they will have the business service in it. So but the reason is, I promised Sendil that I won't touch Wi-Fi 6 in this particular seminar. So I would want to leave to that word. But hopefully I answered that question for you.
Yeah, no, I got it. Yeah, thanks a lot. Yeah. Any other questions? We have a couple of minutes left.
So I have one question. This is Arpan.
Please go ahead.
So when can we expect some kind of deployment of intelligent reflected surface-based Wi-Fi network or cellular network? Any thoughts?
Intelligent, I did not get the.
Intelligent reflected surfaces.
I am not aware of it. Sorry.
Okay, so these are basically meta surfaces which can be programmed, and by doing that, actually you can control the reflectivity, and you can do beamforming and other stuff.
Okay.
At least I'm not aware of it. Sorry.
Okay.
Maybe something which I learned. I'll track it.
Okay, thanks.
It's being
Okay.
considered for implementation by some players, but I think this is still work in progress, if I may say that. I'm at least aware of like a couple of Korean companies which are actually investing and working on this particular technology. They haven't made any lead yet in a massive scale, right? So definitely in labs they are seeing some performances, but not something which is demonstrable yet. So hopefully in the next 2-3 years you will actually see meta surfaces and other things promising.
Okay, Nadeem, I think if
Yeah.
there is no other question, then you can proceed with your concluding remarks.
Yeah.
And thanks to everybody for attending. And so this was the last session of COMSNETS 2021. So
Vinosh, can you hand over the screen to me?
Sure.
So thank you, Vinosh and Sendil, for the excellent talk. I know it's a 3-hour presentation, but as Sendil said in the beginning, that the last hour is going to be very interesting. And personally speaking, I found that the last part where Vinosh talked about the things beyond what we read about today, that was very exciting to see how things are shaping up. And I hope all the people who attended the tutorial enjoyed and learned a few new things. I personally did. So thanks to both of you for taking time out and putting together this excellent tutorial. As a token of our appreciation, I just want to flash the mementos that we will mail to you later on. So this is for Sendil for the excellent tutorial session on the 5G NR deployment considerations and its continued evolution in 3GPP, and for Vinosh as well. So thanks to both of you for the.
We don't see you, neither your screen.
That is the perils of Okay, I hope now you can see my screen.
Yes.
Yeah. So this is the recognition for Sendil, and this is our memento for Vinosh. We'll be mailing these to you, Sendil. We don't have your address yet, so we'll be mailing these to you soon. And thanks a lot for everyone who attended, and thanks especially for Vinosh and Sendil for the excellent presentation. Thank you, everyone. Good night. Goodbye.
Thank you. Bye bye.
Thank you.
Bye.
Bye.
Professor Arpan. Bye. Good
Bye.
luck.
Thanks. Good night.
See you, Sendil. I'll catch you later.